From creamy strawberry ice cream to thick Greek yogurt and the layered elegance of tiramisu, each dessert begins as simple ingredients transformed by precise processes. In this video, we explore the step-by-step journey inside the factory, highlighting the machines and freezing that turn dairy into these beloved treats. Fresh strawberries arrive in bulk containers and are immediately transferred onto vibrating sorting tables. The surface trembles in rapid pulses, spreading the fruit into a single layer. Optical scanners sweep across the moving belt, detecting color density and surface irregularities. Jets of compressed air fire in milliseconds, ejecting underripe or bruised berries. The selected strawberries continue forward in a uniform stream. The fruit drops into a rotating drum washer. High-pressure sprays strike from multiple angles, stripping away soil and field residue. The drum slowly turns, ensuring every surface is exposed to the water jets. Excess water drains through perforations while the berries advance toward the discharge chute. A final mist rinse removes remaining particles before the fruit exits onto a dewatering conveyor lined with absorbent rollers. Next, the strawberries pass beneath stainless steel blades that remove stems with precise vertical cuts. The trimmed berries fall into a stainless hopper, feeding an industrial crusher. Inside the crusher, rotating paddles press the fruit against a perforated screen. The flesh collapses into a thick pulp, releasing juice and seeds. The sound shifts from a soft tumble to a wet grinding hum as the texture transforms into a uniform mash. The pulp moves into a heated processing tank equipped with a slow-turning agitator. Granulated sugar is metered in through a screw feeder. The agitator sweeps through the mixture, dissolving sugar crystals into the strawberry mass. Gentle heat intensifies the aroma while evaporating excess moisture. The mixture thickens slightly as soluble solids increase. A refractometer probe continuously measures sugar concentration, adjusting feed rates to reach precise sweetness. Once balanced, the strawberry blend flows through a fine mesh filter. Seeds and fibrous fragments are separated, producing a smooth puree. The filtered puree enters a vacuum deaerator, where trapped air bubbles rise and collapse under reduced pressure. The surface briefly foams, then settles into a glossy, uniform liquid. This step prevents oxidation and preserves the bright red hue. Parallel to fruit preparation, the dairy base begins in large insulated tanks. Fresh cream and whole milk are pumped in controlled proportions through stainless pipelines. Load cells beneath the tanks monitor weight to ensure exact ratios. Liquid sugar syrup joins the blend through automated valves, eliminating undissolved crystals. The mixture swirls under high-speed agitators, forming a homogeneous liquid. Milk solids and stabilizers are introduced through a powder induction system. Fine powders are drawn into the vortex created by the spinning mixer, preventing clumping. The stabilizers hydrate gradually, thickening the base and improving body. The sound of the mixer deepens as viscosity increases. Temperature sensors regulate the mixture to maintain optimal hydration conditions. The blended dairy base is pumped into a plate heat exchanger for pasteurization. Thin layers of liquid flow between heated stainless plates. Hot water circulates on the opposite side, raising the temperature rapidly. The mixture reaches pasteurization temperature within seconds and is held briefly in a holding tube. This precise thermal treatment eliminates unwanted microorganisms while preserving flavor integrity. Immediately after heating, the mixture travels back through the heat exchanger, where chilled water cools it down quickly. The rapid drop in temperature prevents overcooking. The base exits at a cold, controlled temperature and flows into aging tanks. Inside these tanks, slow paddles rotate gently, preventing separation while allowing fat molecules and proteins to stabilize. Over several hours, the mixture thickens slightly as fat crystallizes and stabilizers fully hydrate. Once aged, The dairy base is directed toward a high-pressure homogenizer. The liquid is forced through microscopic openings under intense pressure. Fat globules shatter into tiny droplets, dispersing evenly throughout the mixture. The texture becomes smoother and more stable. The transformation is audible as a sharp hiss accompanies the sudden pressure release. The homogenized base and the prepared strawberry puree converge in a blending tank. Automated flow meters synchronize their entry to achieve the desired fruit concentration. As they merge, rotating blades fold the red puree into the pale dairy liquid. The color shifts from off-white to a uniform pink. The mixture thickens slightly as fruit solids integrate with the cream structure. The combined mixture flows into a continuous ice cream freezer. Inside the cylindrical freezing barrel, refrigerant circulates around the outer shell, drawing heat away rapidly. A dasher spins within the barrel, scraping frozen layers from the inner wall. The scraping action prevents large ice crystals from forming. Simultaneously, controlled air is injected into the mixture. Tiny air bubbles disperse evenly, increasing volume and creating a light texture. As the mixture churns, it transforms from liquid to semi-solid. The texture resembles soft snow. Temperature probes monitor the freezing point continuously. The dasher blades slice through the thickening mass with rhythmic precision, producing a steady mechanical hum. Within minutes, the ice cream reaches a soft serve consistency and is extruded from the barrel through a nozzle. For varieties containing strawberry pieces, an inclusion feeder introduces diced fruit at this stage. The small cubes drop into the flowing stream and are folded gently by a low-speed auger. The movement distributes the pieces evenly without crushing them. Bright fragments remain suspended in the creamy matrix. The semi-frozen ice cream moves through insulated pipes into filling machines. Containers travel along a conveyor beneath multi-nozzle fillers. Each nozzle descends and releases a measured volume. The soft ice cream spirals into the container, forming layered folds. Vibrating plates beneath the conveyor remove trapped air pockets and level the surface. Lids are placed automatically by a rotary placer. A brief downward press seals each container. Date codes are printed in precise black ink on the lid surface. The filled units advance into a hardening tunnel. Inside, powerful fans blast air at extremely low temperatures. The air circulates at high velocity, stripping remaining heat from the product. During hardening, ice crystals stabilize into a fine structure. The temperature at the core drops steadily until the entire mass becomes firm. The transformation locks in the overrun and prevents structural collapse. The containers exit the tunnel, solid and rigid. They pass through a metal detection system that scans each unit for metallic fragments. A reject arm removes any container that fails the scan. Approved units continue to a cartoning station where multiple containers are grouped and wrapped in printed sleeves. Mechanical arms fold cardboard around the stack with crisp, angular movements. The cartons move onto a palletizing line. Robotic arms lift entire layers and stack them with geometric precision. Each layer aligns perfectly, forming a stable cube. Stretch film wraps tightly around the stacked load, binding it into a single secure mass. Before storage, samples from each batch are tested in a texture analyzer. A probe presses into the frozen ice cream, measuring resistance and consistency. The data confirms proper freezing and air incorporation. Color sensors verify uniform pink tones, ensuring the strawberry dispersion is consistent. Throughout the entire process, stainless steel pipelines connect every stage. Pumps pulse rhythmically, maintaining continuous flow. Valves open and close in timed sequences controlled by automated systems. Digital panels display temperatures, pressures, and flow rates in real time. Each transformation occurs in a precise order, from raw fruit and liquid dairy to aerated frozen structure. The final packaged strawberry ice cream rests in cold storage at stable sub-zero temperatures. Inside each sealed container, microscopic ice crystals, evenly distributed air cells, stabilized fat droplets, dissolved sugars, and concentrated strawberry solids form a balanced matrix. The journey from whole berries and fresh cream to smooth frozen dessert is defined entirely by controlled motion, measured heat exchange, rapid freezing, and exact mechanical coordination. Raw milk is delivered to the processing facility in insulated stainless steel tanks. Upon arrival, the milk is passed through a series of mesh strainers to remove any large particulate matter. It then flows into a balance tank, where load cells continuously measure the volume and ensure accurate downstream processing. The temperature of the milk is monitored by inline thermocouples, confirming it is within a range suitable for further processing. The milk proceeds to a clarification step. High-speed centrifuges spin at thousands of revolutions per minute, using centrifugal force to separate any remaining somatic cells, small debris, or micro-impurities. Clarified milk exits the centrifuge through a continuous discharge system, maintaining a smooth, consistent flow. The removal of these particles ensures uniformity in subsequent heating and fermentation stages. Next, the milk enters a standardization phase. Skim and cream fractions, measured precisely by flow meters, are blended to achieve the desired fat content for Greek yogurt. The mixture passes through automated mixers that homogenize the dairy liquid, dispersing fat droplets uniformly to prevent separation and ensure a smooth, final texture. Homogenization is critical for creating a thick, creamy mouthfeel after fermentation and straining. The standardized milk then undergoes pasteurization. It flows through a plate heat exchanger where thin layers of milk pass between heated stainless steel plates. Hot water or steam circulates on the opposite side, rapidly raising the temperature to a controlled level, typically around 85 to 90 degrees Celsius. The milk is held at this temperature in a holding tube for several seconds to destroy pathogenic bacteria and deactivate enzymes. Pasteurization ensures safety and stabilizes proteins for improved coagulation. Immediately after pasteurization, the milk is cooled rapidly via the same heat exchanger in counterflow, using chilled water or glycol to bring it down to the fermentation temperature, typically around 42 to 45 degrees Celsius. Rapid cooling prevents overcooking the proteins and preserves a neutral flavor profile, readying the milk for bacterial culture inoculation. The milk then flows into fermentation tanks. Starter cultures containing specific strains of Lactobacillus bulgaricus and Streptococcus thermophilus are introduced in measured doses. Automated dosing systems ensure exact quantities of active cultures are dispersed evenly. The milk is gently agitated to distribute the bacteria uniformly without creating excessive air bubbles, which could interfere with texture development. Fermentation begins as the tank is held at controlled temperature. Heating jackets or circulating water jackets maintain constant warmth. The bacteria metabolize lactose into lactic acid, gradually lowering the pH of the milk. As acidity increases, casein proteins destabilize and aggregate, forming a gel network. The process is monitored via inline pH sensors, which track the decrease in pH toward the target range, typically between 4.5 and 4.6. During fermentation, slow, intermittent stirring ensures uniform heat distribution and prevents a dense skin from forming on the surface. The gel forms gradually, transforming the liquid milk into a soft, viscous curd. The curd's elasticity is assessed through viscometers or occasional manual sampling to determine the readiness for straining. After the curd reaches the desired acidity and consistency, fermentation ceases by cooling. The tanks are chilled using recirculated cold water or brine jackets, rapidly bringing the yogurt to around 4 degrees Celsius. Cooling halts bacterial activity, stabilizes the gel network, and prevents over-acidification. The cooled yogurt now has a creamy, spoonable texture, but is still high in whey content compared to traditional Greek yogurt. The next stage is straining, which is critical to producing Greek yogurt's characteristic thickness. The yogurt is pumped into centrifugal separators or stainless steel sieves equipped with fine mesh filters. Mechanical pressure or centrifugal force separates liquid whey from the solid curd. In some systems, vacuum-assisted filtration accelerates whey removal while maintaining the integrity of the protein matrix. The result is a dense, creamy yogurt with concentrated milk solids. For large-scale production, the strained yogurt may pass through multiple sequential centrifuges or filters to achieve the target consistency. Each stage incrementally removes whey, reducing moisture content and increasing protein concentration. The sound of liquid passing through perforated plates and the gentle hum of centrifugal rotors indicate continuous separation. Monitoring instruments track moisture levels and protein content to ensure consistency batch to batch. After straining, the thickened yogurt may be blended briefly to homogenize texture. Low shear paddle mixers fold the curd gently, eliminating pockets of firmer or looser gel while avoiding aeration that could introduce unwanted air bubbles. The texture at this point is dense but smooth, with a uniform pale white color. If flavoring or fruit inclusions are desired, they are introduced in a separate blending stage. Natural fruit purees, syrups, or flavor extracts are metered into the thick yogurt using precision dosing pumps. Rotating augers fold these additives gently, maintaining the yogurt's viscosity while achieving even distribution. Inline mixing sensors ensure consistent blending without breaking the gel network. The yogurt then moves to filling equipment. Containers travel along conveyors beneath precision nozzles that deposit exact volumes. The yogurt flows in a continuous stream or spirals into the containers, forming a smooth surface. Vibrating platforms may gently level the yogurt and remove trapped air bubbles, preventing voids that could affect shelf appearance and texture. Filled containers pass through automated capping systems. Lids are sealed with controlled pressure, ensuring airtight closure. Date coding machines print batch information directly on the lid surface. The sealed units are then conveyed into cold storage chambers. Rapid cooling continues as the yogurt is brought down to storage temperature, typically around 0 to 4 degrees Celsius. This step further stabilizes texture, slows bacterial activity to preserve shelf life, and maintains product integrity during handling. Temperature-controlled conveyors and chill tunnels ensure minimal fluctuation, maintaining the thick, creamy structure of the Greek yogurt. Throughout the production line, stainless steel pipelines connect tanks, filters, and filling machines. Pumps regulate flow rate, while automated valves open and close in precise sequences. Sensors continuously monitor flow, temperature, pH, and protein content, providing real-time data to the control system. Any deviation triggers adjustments to maintain consistent product quality. During quality control, samples are drawn from various points along the line. Rheometers measure viscosity, ensuring the yogurt meets textural specifications. Moisture analyzers confirm the whey content aligns with Greek yogurt standards. Colorimeters check for uniformity in hue and brightness. Microbiological tests verify that bacterial counts are within acceptable ranges, confirming proper fermentation and pasteurization effectiveness. The final product exhibits a dense, creamy texture with minimal whey separation. Protein concentration is high, a result of controlled straining and careful homogenization. The yogurt retains a subtle tang from lactic acid development and, if included, uniform fruit dispersion or flavor infusion. Containers are stacked and wrapped for storage, ready to maintain their structure until distribution. Robotic palletizers lift layers of containers and stack them with precise alignment. Stretch film wraps the pallet, securing it for cold transport. Throughout handling, the Greek yogurt remains chilled, preventing separation or texture degradation. Each pallet holds hundreds of containers, reflecting the cumulative precision of pasteurization, fermentation, straining, blending, and packaging. Every stage of the process emphasizes mechanical control and precision. From raw milk clarification through homogenization, controlled fermentation, whey removal, and final packaging, the production relies on continuous monitoring of temperature, pH, viscosity, and moisture. The interplay of mechanical devices, centrifuges, mixers, heat exchangers, pumps, and filling machines ensures consistency, texture, and protein concentration in every batch. The journey from liquid milk to thick, creamy Greek yogurt is defined by sequential transformations: purification, fat standardization, heat-induced protein denaturation, bacterial fermentation, gel formation, controlled cooling, whey separation, and gentle blending. Each transformation is quantified and monitored, producing a stable, high-protein yogurt with characteristic density and smoothness. Even at microscopic scale, the structure is precise. Fat. Droplets are homogenized and dispersed. Protein networks form consistent matrices, and tiny air pockets are minimized. Whey removal concentrates solids without fracturing the gel. The final yogurt exhibits uniform texture, flavor, and acidity due entirely to controlled mechanical and thermal processes. Mascarpone cheese arrives in insulated tanks and is first examined for temperature and consistency. The cheese is pumped through stainless steel pipelines into a blending vat. High shear agitators rotate within the vat, dispersing the dense cheese uniformly and ensuring no lumps remain. The mixers are equipped with variable speed motors, allowing precise control of shear forces to maintain the creamy texture without aerating excessively. Load cells beneath the vat monitor the mass of cheese entering the mixer to confirm exact quantities for recipe consistency. Egg yolks are separated mechanically using rotary egg breaking machines. The eggs are cracked, and yolks and whites are divided using centrifugal separators. Yolks are collected in stainless steel hoppers and gently pumped to pre-blending tanks. Inline viscometers monitor the viscosity of the yolk stream, ensuring smooth, homogeneous flow before incorporation. Sugar is introduced via screw feeders, passing through heated hoppers to prevent clumping. Paddle agitators fold the sugar into the yolks gradually, allowing partial dissolution and formation of a light, smooth custard base. The mascarpone is folded into the yolk-sugar mixture using low-speed planetary mixers. Rotating arms sweep through the mixture, gently folding the dense cheese into the custard without incorporating air. Sensors track torque on the mixer shafts, providing data on viscosity progression. Once fully integrated, the mixture has a uniform, glossy appearance and a controlled thickness that will later allow it to layer effectively in the final dessert. Separately, espresso coffee is brewed continuously. Water is pumped into high-pressure stainless steel extraction units at precisely 92 to 95 degrees Celsius. Ground coffee is metered into portafilters or drum roasters, compacted by mechanical tampers. Pressurized water flows through the grounds at a controlled rate, extracting soluble solids and aromatic compounds efficiently. The resulting espresso flows into holding tanks equipped with heat jackets to maintain temperature until required for soaking. A continuous conveyor system moves the espresso from brewing to the soaking station with minimal exposure to air, preserving flavor integrity. Optional liqueurs, such as coffee-flavored or almond-based spirits, are stored in temperature-controlled tanks. Flow meters regulate the addition of liqueur to the espresso in mixing tanks. Static mixers create a homogeneous coffee liqueur blend, maintaining precise flavor ratios. The mixture passes through inline thermometers, ensuring it is at a temperature that will saturate the ladyfinger biscuits without prematurely softening them. Ladyfinger biscuits are produced separately. Flour, sugar, eggs, and leavening agents are combined in a high-speed mixing ribbon or planetary mixer. The batter's viscosity is monitored by inline rheometers to ensure it is thick yet pourable. Once mixed, the batter is extruded through nozzle systems onto conveyor belts in uniform finger shapes. The fingers pass through tunnel ovens with controlled zones of convection and infrared heating, baking them to a firm yet spongy consistency. Cooling conveyors allow the biscuits to reach ambient temperature while retaining flexibility for soaking. The cooled ladyfingers are transferred to an automated soaking line. Conveyors align the biscuits in single layers beneath nozzles that dispense measured volumes of coffee liqueur mixture. The liquid jets impact the biscuit surface precisely, soaking the exterior without disintegration. Vibrating trays under the nozzles gently shake the biscuits, promoting uniform absorption. Sensors track moisture content in real time, adjusting nozzle flow rates and conveyor speed to achieve consistent saturation across all units. After soaking, the biscuits are deposited into filling trays by robotic arms or gravity-fed systems. The trays are designed with cavities corresponding to the final product size. Each cavity receives a layer of soaked ladyfingers, forming the base layer of the tiramisu. Sensors confirm correct placement, detecting misaligned or broken biscuits, which are automatically removed from the line. The mascarpone yolk sugar mixture is then transferred to depositing machines. Multi-nozzle filling heads extrude precise amounts over the biscuit base. Linear actuators and programmable logic controllers coordinate nozzle motion to spread the mixture evenly. Low-speed paddles may be used after deposition to smooth the layer without incorporating air, preserving the dense, creamy texture characteristic of tiramisu. If multiple layers are required, the process repeats. Another layer of soaked ladyfingers is added atop the mascarpone layer, followed by additional cheese mixture deposition. Robotic arms and precision conveyors ensure exact alignment of layers, avoiding displacement or uneven thickness. Inline laser sensors monitor height and uniformity across the tray, signaling adjustments in deposition volumes to maintain consistency batch to batch. Cocoa powder application occurs once all layers are complete. Fine mesh sifters deliver a controlled dusting of cocoa over the surface. Pneumatic shakers or vibrating plates assist in evenly distributing the powder, preventing clumping or excessive coverage. In large-scale production, automated dispensing heads move across the tray to maintain a uniform layer of cocoa, forming the characteristic top finish of the tiramisu. Color sensors verify the evenness and intensity of the cocoa layer. Completed trays proceed to refrigeration tunnels. Cold air circulates at high velocity, rapidly bringing the product down to approximately 4 degrees Celsius. The cooling process is gradual enough to preserve the gel structure of the mascarpone layer, but fast enough to stabilize moisture in the ladyfingers. Fans and airflow deflectors maintain uniform temperatures across trays, preventing condensation or uneven chilling. During storage and transport, trays remain in temperature-controlled environments. Sensors monitor core temperatures to ensure the mascarpone mixture remains firm without freezing. Refrigerated conveyors maintain orientation and prevent tilting, which could disrupt layered structure. Shock-absorbing supports minimize vibrations, preserving the integrity of delicate layers during handling. Before packaging, automated vision systems inspect each tray. Cameras detect layer uniformity, surface smoothness, and cocoa distribution. Deviations beyond preset tolerances trigger removal or correction of the tray. This ensures that the visual appearance aligns with specifications. Weight sensors confirm that each tray contains the correct mass of ingredients, compensating for minor variations in deposition or biscuit absorption. Once inspection is complete, trays move to sealing stations. Transparent film or lids are applied using mechanical arms with pneumatic actuators. Vacuum or controlled atmosphere sealing may be applied in some systems to extend shelf stability without altering texture. Labeling machines print batch codes, production dates, and other required data on lids or shrink sleeves, using high-resolution thermal printers synchronized with conveyor motion. Finished and packaged tiramisu trays are then conveyed to palletizing robots. Each layer of trays is stacked systematically, maintaining geometric stability. Stretch film is applied in tight spirals around the stack to secure pallets for refrigerated storage. Temperature and humidity sensors within the storage area ensure that the dessert maintains optimal conditions until distribution. Refrigerated transport. Systems continue this temperature-controlled environment, preserving texture, flavor, and visual quality. Throughout production, stainless steel pipelines connect each step: cheese preparation, egg blending, coffee brewing, biscuit soaking, layering, and packaging. Pumps regulate flow, while automated valves control timing and volume precisely. Temperature probes, viscosity meters, pH sensors, and weight scales provide real-time data to the central control system, allowing fine adjustments in process parameters without manual intervention. Each transformation, from raw cheese and eggs to layered cocoa top dessert, relies on precise mechanical and thermal control. Optional flavor modifications, such as chocolate shavings or alternative liqueur blends, are introduced at designated stages using metered dispensers. High-speed augers fold additives into the mascarpone mixture without breaking the gel, ensuring uniform distribution. When applied to the surface, sprinkling systems position toppings precisely without disturbing the layers below. Quality assurance tests occur at multiple stages. Rheometers evaluate the spreadability and firmness of the mascarpone mixture. Moisture analyzers verify that ladyfingers retain enough liquid to be soft but not soggy. Refractometers measure sugar concentration in both the custard and coffee liqueur blend. Visual inspection ensures color consistency, and spot microbiological sampling confirms the effectiveness of pasteurization and safe storage. The final product exhibits precise physical properties: a dense yet creamy mascarpone layer with stable gel structure, a sponge layer of ladyfingers soaked to optimal moisture content, and a fine cocoa powder surface finish. The internal protein and fat matrix supports the structure while retaining a soft, spoonable texture. Each spoonful reflects careful coordination of ingredient ratios, temperature, shear forces, and layer integration. Even at a microscopic level, the structural integrity is controlled. Proteins in the mascarpone form a cohesive network, trapping air minimally. Fat droplets are distributed evenly, and moisture from coffee infusion is absorbed uniformly in the sponge layer. Cocoa particles adhere lightly to the top without penetration, ensuring visual consistency and flavor profile. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, the open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the cream filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix, while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. Formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. Airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labeled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron-level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. Molten butter streams across a sheet of dough, the first movement in the making of a croissant. Inside a modern factory, the air smells like yeast and warm flour, rich and comforting. But the scene is less like a bakery and more like an engineering lab. Stainless steel rollers, climate-controlled rooms, sensors, and conveyors stretching as far as the eye can see. Each golden, flaky croissant begins here in a choreography of temperature, timing, and touch, designed to turn flour, water, butter, sugar, and yeast into hundreds of delicate layers that rise and shatter with every bite. It starts with the dough. In an enormous spiral mixer, hundreds of kilograms of flour pour in from overhead silos, joined by measured streams of water, milk, sugar, salt, and blocks of softened yeast. The machine hums steadily, kneading the mixture into a smooth, elastic mass. The balance here is precise. Too little water, and the dough tears during rolling. Too much, and it turns sticky and uncontrollable. Sensors inside the mixer measure torque and resistance, automatically adjusting speed until the dough reaches exactly the right consistency. Stretchy, but not tough. As the mixer spins, the smell of fermentation begins to bloom. Sweet, faintly alcoholic, and alive. After about 10 minutes, the dough is released into a trough and left to rest. This resting stage, called bulk fermentation, allows the gluten to relax and the yeast to awaken. The dough rises slowly, filling the air with carbon dioxide bubbles that will help form the delicate crumb later. While it rests, butter is prepared. croissant butter isn't just any butter. It's high in fat, low in moisture, and chilled to an exact temperature, usually between 12 and 16 degrees Celsius. At this stage, butter behaves more like clay than fat. It bends, doesn't crack, and can be shaped into perfect sheets. In the factory, large blocks are pressed through rollers until they form thin slabs as wide as the dough itself. Workers refer to this step as tempering the butter, but in truth, it's all about physics. The butter must be soft enough to fold, but firm enough not to melt when it meets the dough. The next step is lamination, the art that defines croissants. On the laminator, a massive conveyor stretches out like a runway, often over 15 meters long. The dough, now rested and pliable, rolls out into a wide rectangle several centimeters thick. A mechanized arm lays the butter sheet directly on top, perfectly centered, then folds the dough over it like an envelope. Hydraulic rollers compress the layers together gently, sealing the butter inside. This laminated block now begins its transformation into hundreds of layers. It passes through rolling machines that lengthen and flatten it, then folding stations that double or triple it repeatedly. Each fold multiplies the number of layers exponentially, from 2 to 4, 4 to 8, 8 to 16, until the dough contains up to 81 wafer-thin strata of butter and dough. Between each pass, the sheet travels through a cooling tunnel, chilled to just above freezing. This keeps the butter firm, preventing it from blending with the dough. Without that temperature control, the butter would melt and leak out, destroying the structure before baking. The sound of the lamination room is constant. Rollers whirring, compressors humming, dough sheets flapping lightly against steel. The air smells faintly of butter and flour, and everything glistens under the bright lights. Workers monitor thickness gauges and adjust tension controls, ensuring every sheet remains perfectly even across its width. A difference of 0.5 millimeter could alter the final texture dramatically. Once laminated, the dough rests again to relax the gluten, then it's time for shaping. Massive guillotine cutters slice the sheets into long triangles, each destined to become one croissant. The triangles travel on conveyors toward an automated rolling machine. There, a soft brush flicks off excess flour, and mechanical fingers gently grip each triangle's base. The belt moves forward, and the dough rolls onto itself 3 times, tucking the tip under neatly. In a blur of motion, hundreds of croissants take shape every minute, each one coiled with perfect precision. If the croissant line includes filled varieties like chocolate or almond, the process adjusts. Before rolling, the machine places thin chocolate batons or a measured dollop of almond paste along the base of each triangle. The filling line operates with the precision of a printing press, dropping identical portions at high speed. The rest of the dough wraps around them seamlessly, encasing the filling without bursting the layers. After shaping, the croissants rest on trays or conveyor racks that move toward the proofing chambers. These are warm, humid rooms that mimic the gentle conditions of a traditional bakery, but on an industrial scale. Inside, the temperature sits around 27 degrees Celsius, with humidity near 80%. Over the next 45 to 90 minutes, the yeast gets to work again. Each croissant swells as gas pockets expand between the butter layers. The smell here is intoxicating. Butter, sugar, and yeast mingling into something unmistakably pastry-like. Proofing is a fragile stage, too short, and the croissants bake dense and heavy, too long, and they overexpand, bursting during baking. Computers monitor the chambers constantly, adjusting airflow and humidity in real time. Infrared sensors scan the trays, measuring surface growth and evenness. When the data shows the exact rise in volume, the trays move automatically toward the next step, baking. Before entering the ovens, the croissants pass beneath a misting station. A thin spray of egg wash, beaten yolks mixed with milk, coats the surface. This is what creates the iconic golden sheen and crisp exterior. The spray nozzles move back and forth in perfect rhythm, applying an even glossy layer. The air in this area smells rich and savory, the first hint of what's about to come. The ovens themselves are enormous tunnels, often over 20 meters long. Conveyor belts carry thousands of croissants through zones of precisely controlled heat. The first zone is hot, around 230 degrees Celsius, to trigger oven spring. The explosive expansion caused by steam from both the butter and dough. The next zones lower gradually, allowing the layers to set and brown evenly without burning. As the croissants bake, butter melts and vaporizes, forcing the dough layers apart into crisp, airy sheets. The factory fills with the unmistakable aroma of caramelizing butter and toasting flour, a smell that can travel hundreds of meters through ventilation ducts. By the time they exit the oven, the croissants are deep golden, hollow sounding when tapped, and flaky enough to shed crumbs even in the conveyor's motion. Cooling fans blast them with filtered air, stabilizing the crust and stopping the baking process instantly. The sound is like a soft rustle, a million tiny flakes settling at once. Some croissants are sold plain, while others continue to specialized lines for glazing or filling. For glazed versions, conveyors carry them under cascading curtains of apricot jelly, brushed thin for shine. For filled varieties, like custard or hazelnut cream, injectors pierce the base with tiny nozzles, depositing precise amounts into the center. Each injector operates under pressure, filling without collapsing the delicate interior. Once cooled, the croissants head for packaging. Robotic arms arrange them into rows, aligning the curved ends uniformly before feeding them into form and seal machines. Plastic films wrap around them, sometimes with nitrogen gas flushed inside to preserve freshness. The sealed packs move to labeling stations, where date codes and batch numbers are printed automatically. Each batch can be traced back to the exact moment it was mixed, proofed, and baked. For frozen croissants, common in large-scale operations, the process diverges just before baking. Instead of entering the oven, proofed doughs are quickly flash frozen at -40 degrees Celsius in spiral freezers. This locks in their structure, suspending yeast activity until baking. Bakeries and cafes around the world then bake them fresh on site, recreating the aroma and texture as if they just left the factory oven. A bagel begins its life as a lump of dense, sticky dough. Nothing elegant, nothing glossy, just raw potential waiting for transformation. Inside a modern bagel factory, the smell hits first. The sharp tang of yeast, the warmth of baked flour, and the faint sweetness of malt syrup hanging in the humid air. Around it all, machinery hums with steady rhythm. Mixers, kettles, conveyors, each one part of a process that turns those rough masses of dough into thousands of golden, chewy rings every hour. The process begins with flour. Strong, high-protein flour, the kind that can stand up to kneading and boiling without collapsing. Bagels demand structure, so the protein content hovers around 13 to 14%, higher than for most breads. From towering silos above the factory floor, measured streams of flour pour into giant horizontal mixers. Along with the flour comes water, yeast, salt, sugar, and, most importantly, malted barley syrup, which gives bagels their signature flavor and color. As the mixing starts, the dough fights back. It's stiff, resisting the machine's spiral arms, which churn and pull against it with deep, rhythmic groans. The resistance is intentional. Bagel dough uses less water than ordinary bread, creating a low hydration mix that bakes up dense and chewy rather than light and fluffy. Inside the bowl, friction from the metal beaters raises the temperature, warming the yeast just enough to wake it up. After about 10 minutes, the dough forms a heavy, elastic mass that stretches but doesn't tear, a living, breathing network of gluten strands. Once mixed, The dough is tipped out onto a conveyor and divided into massive blocks that rest under plastic covers. This rest period, called floor time, allows the gluten to relax and the yeast to begin fermenting. It's here that flavor begins to build. Even in a factory, the process can't be rushed. The dough needs time for the yeast to produce tiny bubbles of gas and faintly sour notes that will deepen during baking. The air in this section of the plant smells unmistakably like a bakery. Warm, doughy, and slightly sweet. When the dough is ready, it moves to the divider. This machine cuts the heavy blocks into smaller portions, each the exact weight of a finished bagel. Precision here is key. Even a few grams difference would cause uneven baking later. From the divider, each portion passes into a former, a set of rotating drums that shape it into a smooth cylinder, then poke a hole through the middle and seal the ends together. It happens so fast that the human eye can barely catch it. A raw bagel, perfectly round and uniform, drops onto a conveyor every half second. Older methods formed bagels by hand, rolling the dough into ropes, twisting, and joining the ends. But in a modern plant, the process has been mechanized to stunning precision. Still, the principle is the same. That central hole isn't decoration. It's functional, allowing the bagel to cook evenly when boiled and baked, and letting heat penetrate quickly in the oven. The freshly formed bagels now travel slowly on conveyor trays toward the fermentation room. Here the air is warm and moist, typically around 30 degrees Celsius with 70% humidity. The dough proofs gently for about 20 to 30 minutes, enough for the yeast to puff it up slightly, but not enough to turn it fluffy. Bagels are meant to be firm, not airy, and the factory controls this by limiting fermentation time. Sensors monitor the temperature constantly, while cameras track the rise of each batch. After proofing, the trays glide towards one of the most distinctive stages in the process: boiling. This is what separates bagels from all other breads. At the heart of the factory, massive kettles simmer with water infused with barley malt and a touch of sugar. Steam rises in fragrant clouds, and workers in protective aprons monitor the rolling bubbles. The proofed bagels slide down metal chutes into the water, bobbing like small buoys. They stay submerged for less than a minute, just long enough for the starches on the surface to gelatinize. This boiling step locks the crust, sealing in moisture and giving bagels their signature chew. Some factories use conveyor kettles, long troughs of hot water with moving mesh belts that carry the bagels through automatically. The sight is hypnotic. Hundreds of pale rings drifting through shimmering heat, their surfaces turning slick and glossy. When the bagels emerge, they're slightly puffed, firm to the touch, and ready for toppings. Wet surfaces are ideal for adhesion, so this is the perfect moment for flavor coatings. The freshly boiled bagels pass under rotating drums that shower them with sesame seeds, poppy seeds, dehydrated onion flakes, or coarse salt. For everything bagels, multiple topping feeders align in sequence, releasing their ingredients in overlapping bands. Each sprinkle is calculated to the gram. Cameras and weight sensors verify coverage. Too few seeds, and the bagel looks bare. Too many, and they'll burn in the oven. The topped bagels then head for the ovens. Industrial bagel ovens are enormous tunnel systems, some stretching more than 20 meters long. The first zone blasts intense heat over 250 degrees Celsius to trigger oven spring. Steam nozzles inject bursts of moisture to help the crust develop its signature shine. As the bagels move deeper, the temperature gradually lowers to bake the interior evenly without burning the seeds or toppings. The smell at this point is intoxicating. Roasted malt, caramelized sugar, and nutty flour blending into something unmistakably New York style. The bagels roll out of the oven in golden rows, their crust firm but still slightly pliable. Cooling conveyors carry them upward in looping spirals, allowing air to circulate evenly for about 20 minutes. This cooling phase is crucial. Too fast, and the crust wrinkles, too slow, and condensation makes them soggy. The sound in the cooling area is a soft, rhythmic whisper, fans humming, conveyors rattling lightly, and the occasional crackle of crusts settling as they cool. If the factory produces sliced bagels, they pass through slicing machines once cooled. The bagels ride along upright conveyors where spinning blades split them almost, but not completely, in half. Laser sensors align each cut to the bagel's natural seam, minimizing crumbs and keeping the halves attached for packaging. In some lines, bagels are then toasted lightly for pre-baked versions sold in frozen form. For fresh bagels, the journey continues directly to packaging. Robotic pickers, grippers fitted with soft silicone pads, lift and group them into neat stacks. Every dozen bagels form a perfect ring of golden crusts, ready for wrapping. Bags descend from automated rollers, filling and sealing with quick bursts of compressed air. The warm bagels disappear inside clear plastic, the smell sealed in just before it escapes. Each package receives a printed label with date codes, batch numbers, and timestamps, linking it back to the exact flour lot and mixing cycle. The entire process, from mixing to packaging, happens in less than 3 hours. Yet every step balances chemistry and craft. Bagel dough, though simple, behaves differently from any other bread. Its low hydration and boiling stage create a dense crumb, while the malt sugars caramelize during baking to give that deep brown crust. Factories maintain tight control over every variable: the pH of the water, the protein content of the flour, the concentration of malt syrup, even the mineral hardness of the local water supply. Every detail affects chewiness and color. Automation doesn't eliminate artistry, it refines it. Skilled operators know by sight and sound when something's off. They can tell from the sheen of the boiled bagels whether the water temperature has dipped, or from the smell of the ovens whether the malt syrup ratio needs tweaking. Computers might run the line, but humans keep its rhythm steady. In larger facilities, production never stops. Mixing, proofing, boiling, and baking run in a continuous loop, 24 hours a day. When one batch enters the oven, another is being shaped, and another is fermenting quietly in the warm air of the proofing room. The plant moves like a heartbeat, steady, cyclical, alive. By the time one shift ends, another takes over without pause, and the bagels keep rolling forward, endlessly. For frozen bagels destined for supermarkets, there's one more step: rapid freezing. After cooling, the bagels enter spiral freezers, where chilled air at minus 40 degrees Celsius circulates in powerful gusts. Within minutes, the moisture inside crystallizes uniformly, preserving the chew and preventing ice buildup. From there, they're sealed in bulk cartons and stored in vast cold rooms, stacked high like golden rings, suspended in frost. A muffin begins not with sweetness, but with sound. The deep, rhythmic churn of an industrial mixer. Inside a muffin factory, stainless steel paddles fold thick batter that glistens under fluorescent lights. The smell is warm even before the ovens start. Butter, sugar, and vanilla drifting through the air in soft waves. It's easy to forget, standing there among conveyor belts and cooling racks, that each simple, golden muffin represents a feat of controlled chemistry and industrial artistry. It starts, as all baking does, with ingredients, but here they arrive by the ton. Silos outside the factory hold fine wheat flour that pours into the production line through pneumatic pipes measured by weight sensors down to the gram. Nearby, liquid sugar and vegetable oil are stored in massive heated tanks, while refrigerated containers hold eggs, milk, and butter. Every ingredient is checked for temperature and consistency before it's allowed into the mix. The goal is uniformity. Every blueberry, every crumb, identical across millions of muffins. The process begins in mixing rooms where large spiral mixers, some capable of handling over 500 kilograms of batter at a time, wait beneath ingredient feeders. The order of addition matters more than most realize. First comes oil or butter, then sugar, which dissolves into it to create a smooth base. Eggs and milk are pumped in next, blending until glossy. Then the dry mix, flour, baking powder, salt, and sometimes a pinch of cornstarch, is sifted in gradually. As the paddles turn, the mixture thickens into the dense, rich batter that defines a muffin. Unlike bread, muffin batter isn't needed to build gluten. In fact, too much mixing would ruin it, making the final texture rubbery instead of tender. Modern machines solve this by using slow, folding paddles that mimic a baker's hand movements. Sensors monitor torque resistance inside the bowl, stopping the mixer automatically the moment the batter reaches perfect viscosity. The result is a smooth, velvety mixture that still holds air bubbles for lift during baking. Once the base is ready, it's time for flavor. Blueberry, chocolate chip, banana nut, double chocolate, each has its own sideline. Through insulated pipes, fruit purees, chocolate drops, or nut pieces are added in precise quantities. High-speed agitators fold them gently to prevent crushing or melting. In blueberry muffins, the berries are often frozen when added. This keeps them intact and prevents the batter from turning purple. Factories even use vibrating screens to separate clusters of berries before mixing, ensuring perfect distribution in every bite. The finished batter flows toward the depositing machines, and this is where the production floor comes alive. Long conveyor belts carry endless rows of paper baking cups that drop neatly into metal trays. Above them, piston depositors pump out exact portions of batter, each a perfect mound, neither too high nor too shallow. These machines work faster than the eye can follow, filling hundreds of molds every minute, each portion within a fraction of a gram of target weight. The smell here is sweet and slightly raw, like cookie dough warmed by friction. Operators in white coats monitor flow rates and cup alignment, adjusting valves and checking viscosity. If the batter thickens over time, a natural effect as air bubbles expand, temperature-controlled jackets around the pipes keep it stable. Every movement is designed to preserve uniformity, because uneven batter means uneven muffins. And that's unacceptable at scale. Once the trays are filled, they pass through a final inspection line. Cameras check that every cup has been filled evenly and that no drips or spills mar the tray. Any flawed portions are rejected automatically, scraped away, and recycled into the next batch. Then the trays disappear into the heart of the operation. The ovens. Industrial muffin ovens are tunnel-like giants, sometimes stretching the length of a bus. Inside, radiant heat and convection airflow combine to bake thousands of muffins at once. The first few minutes are crucial. The batter expands quickly as the water inside turns to steam, pushing against the gluten structure and lifting the dome. In a matter of minutes, the tops crack and rise, forming that familiar golden crown. Steam nozzles near the oven entrance inject controlled bursts of moisture, ensuring the muffins rise smoothly without splitting. The aroma that fills the air here is intoxicating. Sweet butter mingled with caramelizing sugar and a faint edge of vanilla. Workers walking by pause without meaning to, their clothes absorbing the scent. It's the smell of warmth itself. Inside the oven, temperatures start high, around 220 degrees Celsius, then drop gradually through the tunnel to finish baking the interior without drying it out. By the time the trays emerge at the other end, the muffins are fully set, their tops burnished to shades of amber and chestnut. Cooling is next, and it's just as important as baking. The trays roll onto spiral conveyors that wind upward through towers of circulating air. This allows the muffins to cool evenly over 20 minutes, avoiding condensation that would soften their crusts. The gentle hum of fans fills the air, and the muffin's faint crackling can be heard as the tops settle and shrink slightly. The structure is stabilizing, moisture redistributing from crumb to crust, a quiet, invisible process that determines freshness and texture. Once cooled, the muffins are either left in their paper cups or removed, depending on the packaging style. For wrapped muffins, robotic grippers lift them delicately onto parallel conveyors leading to the packaging area. The packaging room is cooler and drier than the rest of the plant. Humidity control is critical to prevent stickiness. Here, muffins destined for individual wrapping enter flow wrapping machines. Plastic film unwinds from massive rolls, forms around each muffin, and seals instantly with a thin line of heat. Nitrogen gas may be puffed inside before sealing, replacing oxygen to preserve freshness and prevent mold. Multi-packs follow a similar path, but are grouped in clusters before wrapping. Machines sort by weight, ensuring that every pack contains identical muffins with matching domes and color. Those intended for supermarket display might be sealed in clear trays with domed lids to protect their shape, while food service batches are bulk packed into lined boxes for cafes and bakeries to finish fresh on site. The entire packaging line operates with mesmerizing precision, conveyors gliding, sealers flashing, robotic arms stacking and boxing. Each bag or tray receives a printed label containing the batch code, oven number, and exact time of production. From there, pallets of warm, wrapped muffins roll toward the shipping docks, bound for distribution centers across the region. For frozen or par-baked muffins, common for export, the process changes slightly. Instead of cooling to room temperature, the trays enter blast freezers immediately after baking. Air at -40 degrees Celsius circulates at high speed, freezing each muffin within minutes and locking in moisture. These frozen muffins will later be thawed and finished in bakeries or hotels, smelling freshly baked even weeks after production. Behind the automation, the science of muffin making is all about balance. Each element, fat, sugar, leavening, flour, affects the final texture. Fat coats flour proteins, limiting gluten formation and keeping the crumb tender. Sugar draws in moisture, helping the muffins stay soft even after cooling. Baking powder and soda release carbon dioxide in two waves, first when mixed, then when heated, giving rise and fluffiness. Temperature, however, is the ultimate master. A shift of even 5 degrees can mean the difference between domed perfection and sunken tops. Factories fight constantly against those tiny variations. Air conditioning keeps the mixing rooms between 18 and 20 degrees Celsius year-round. Liquid ingredients are preheated in winter and chilled in summer to maintain consistency. Even the fruit is conditioned. Blueberries stored at exactly -1 degrees to keep them firm. Chocolate chips kept in coolers so they don't melt before mixing. The result is mechanical perfection that still somehow feels handmade when you peel back the paper and break into one. Chef Boyardee beef ravioli begins its industrial journey with the delivery and preparation of raw ingredients in a tightly controlled, high-capacity food processing environment designed for continuous, large-scale output. At the very start, durum wheat semolina arrives in bulk and is stored in tall silos connected by enclosed pneumatic systems that transport measured amounts of flour into industrial mixing vats. These mixers operate under vacuum to prevent air entrapment in the dough, which could compromise the texture of the final pasta. Water is injected through a flow-regulated system, and the dough is mixed into a dense, elastic mass that is then conveyed into a dough sheeter. Inside this machine, large stainless steel rollers gradually press the dough into a long, uniform sheet of precise thickness. Sensors constantly monitor and adjust roller pressure, sheet thickness, and alignment in real time, ensuring consistent dimensional control across thousands of linear feet of pasta every hour. As the pasta sheet continues on its route, it approaches the forming station. Here, the sheet is split into top and bottom layers using a synchronized cutting system, and the beef filling, prepared simultaneously on a parallel line, is introduced between them. The beef mixture is produced in massive steam-jacketed kettles, where ground beef is cooked with tomato paste, spices, salt, and stabilizers. High-shear mixing blades ensure uniform blending, while thermal sensors regulate the internal temperature to avoid overcooking. Once cooked, the beef filling is transferred to positive displacement pumps that feed the filling directly into the ravioli former. Precise nozzles inject a consistent amount of filling at evenly spaced intervals onto the bottom sheet. The top sheet is laid over it, and the two layers are pressed together by a rotary die that seals and cuts the individual ravioli pockets in one continuous motion. Any excess dough around the edges is collected and recycled back into the dough feeder. The freshly formed ravioli travel along a mesh belt through a par cooking tunnel, where a curtain of low-pressure steam partially cooks the pasta just enough to firm the structure and set the seal. The par cooking chamber is followed by a high-efficiency air chiller that quickly cools the product to prevent further cooking. From here, the ravioli move to the accumulation table that feeds the canning line. The tomato sauce, which is made in a separate set of kettles, is already being prepared in parallel. This sauce includes tomato puree, vegetable oil, spices, and sugar, blended in high-capacity vats, equipped with wall-scraping agitators to ensure uniform cooking and prevent scorching. The sauce is filtered to remove any large solids, skins, or seeds, and is kept hot in jacketed holding tanks while waiting to be dispensed. The canning line is a seamless, high-speed process that brings ravioli and sauce together inside sterilized metal cans. Empty cans are first fed from depalletizers into an inverted position for steam or air sterilization before being returned upright and carried along a conveyor. A timed filling system first drops a preset quantity of ravioli into each can. Next, a separate nozzle dispenses a specific volume of hot tomato sauce into the same can. Load cells and vision sensors measure weight and volume in real time, instantly rejecting any can that falls outside tolerance. To maintain long shelf life, the filled cans receive a quick injection of steam into the headspace to displace oxygen, which is critical for preventing spoilage and discoloration. The cans then proceed to the seaming machine, which applies and crimps the metal lids at high speed using rotary chucks that spin and press the lids into place with a hermetic seal. Once sealed, the cans are routed into a massive rotary retort, a large pressure chamber where the canned ravioli undergo commercial sterilization. This thermal processing step is one of the most critical phases in the entire operation. Inside the retort, the cans are exposed to pressurized steam at temperatures above 121 degrees Celsius for a fixed period, calculated according to product density, can size, and altitude. The process is tightly controlled by a programmable logic controller that adjusts heat input, steam pressure, and timing with precision, ensuring that the interior of each can reach the temperature needed to destroy any potential microbial contaminants. This sterilization method allows the product to be shelf-stable for over a year without the use of chemical preservatives. As the cans exit the retort, they are rapidly cooled using a countercurrent water system that brings the internal temperature down quickly while avoiding thermal shock that could warp the can. After cooling, the cans are dried using air knives that blow off any surface moisture. They then move into the labeling area where each one is printed with a unique production code, expiration date, and batch number using high-speed inkjet printers. These codes are logged in a centralized database that allows full traceability of every can, linking it back to the exact batch of dough, filling, sauce, and sterilization cycle. This traceability system is essential for maintaining quality control and complying with food safety regulations. Labels are applied using rotary labelers, which align the cans, dispense the adhesive-backed labels, and press them smoothly onto the curved surfaces. Any can with a misapplied or missing label is automatically diverted off the line. The labeled cans proceed to the packing station, where they are grouped into shrink-wrapped multi-packs or loaded into cardboard trays, depending on distribution requirements. Robotic arms equipped with vacuum suction heads stack these cases onto pallets in a tightly packed, interlocked pattern that ensures transport stability. Each pallet is weighed, stretch-wrapped, and labeled with a scannable barcode that encodes the full logistics data for shipping and warehouse integration. Completed pallets are conveyed into a climate-controlled warehouse area, where ambient temperature is maintained within a narrow range to preserve product integrity and packaging quality. The inventory system automatically logs each pallet into a virtual grid based on product type, batch, and destination. Orders from distribution centers are matched against inventory using software that assigns retrieval instructions to automated guided vehicles. These vehicles transport the pallets to loading bays where they are prepared for shipment on temperature-managed trucks. Throughout this entire process, every step is monitored by industrial control systems that log thousands of data points per minute, from moisture content in dough to the pressure in the retort chamber. If any sensor detects an anomaly, whether it's a filling inconsistency, temperature deviation, or mechanical irregularity, alarms are triggered, and corrective protocols are initiated automatically. Quality assurance technicians also perform random sampling at every stage, testing dough elasticity, filling viscosity, source pH, seam width, and internal vacuum levels. Any sample that fails a parameter prompts an investigation and potential quarantine of the related batch. The design of this factory setup allows for continuous production for 24 hours a day, with modular maintenance schedules that let individual lines shut down without halting the entire operation. Cleaning in place systems run through every tank, pipe, and pump at regular intervals, using cycles of hot, caustic solution, followed by acid rinses and pure water flushes. This level of automated sanitation prevents bacterial buildup and maintains a sterile environment, especially critical in the post-cook zones. By the time a single can of Chef Boyardee beef ravioli reaches the supermarket shelf, it has passed through dozens of machines and control checks, undergone multiple thermal transformations, and been assembled from raw materials that were processed, cooked, combined, sealed, and sterilized within minutes of each other. The result is a uniform, shelf-stable product that replicates the exact same taste, texture, and aroma across millions of cans each year, a feat of engineering, timing, and integrated automation performed at industrial scale. The industrial production of gnocchi begins with a continuous intake of raw potatoes selected specifically for their starch content, moisture levels, and uniformity. These potatoes arrive in bulk, often delivered in heavy-duty totes or truckloads, and are immediately transferred into stainless steel receiving bins. From here, a water flume system propels the potatoes toward the washing stage using a circulating stream of filtered water, which not only moves the product gently, but also performs a preliminary rinse that separates dirt, rocks, and field debris. The potatoes pass into a rotary drum washer, a large cylindrical cage lined with soft baffles and rotating paddles. Inside, multiple high-pressure spray jets clean the surface of every tuber, while slow drum rotation ensures even exposure. Wastewater is filtered and recycled back into the flume, maintaining efficiency while minimizing fresh water consumption. Once cleaned, the potatoes move onto inclined conveyor belts and pass beneath an optical sorter that detects misshapen or heavily blemished specimens. Air jets eject any defective potatoes instantly. The remaining load proceeds toward the steam peeling chamber, a sealed environment into which high-pressure steam is injected rapidly. This process loosens the skins in seconds without penetrating deeply into the flesh. A sudden pressure drop follows, causing the skins to rupture. As the chamber releases its load, rubber fingers or gentle high-pressure sprayers remove the loosened skin without damaging the underlying structure. The peeled potatoes then travel along a belt for final inspection before cooking. Next, they enter a cooking tunnel equipped with rotary steam ovens or belt-fed boiling sections. These systems are calibrated to cook each potato evenly, using internal probes to track core temperature without overcooking the starch. The cooking time is precisely tuned so the flesh softens just enough for mashing while preserving structural integrity. Cooked potatoes are discharged directly into screw-fed conveyors that deliver them into industrial mashing systems. These mashers force the hot potatoes through perforated plates using rotating paddles, breaking them into a uniform, lump-free mash with consistent density. This mash is transferred into stainless steel hoppers, fitted with agitators to prevent settling while it awaits mixing. Simultaneously, dry ingredients are prepared using a separate set of feeders. Wheat flour, salt, and any dry seasonings are metered in precise ratios using volumetric or gravimetric dispensers, ensuring repeatable consistency across large batches. These dry components meet the hot mash in horizontal ribbon mixers or twin screw extruders, where the dough is developed. If eggs or other binders are used, these are injected through nozzles timed to match the flow rate of the dry and wet components. Dough temperature, torque, and consistency are continuously monitored, allowing automated systems to adjust mixing speed or ingredient dosing in real time. As the dough reaches its final form, it exits into forming lines. These lines are fitted with multi-head extrusion units that shape the dough into cylindrical ropes, which are automatically guided into a cutting module. Guillotine blades or rotary knives slice the ropes into uniform pillow shapes at high speed. Each piece is then transferred onto a vibrating sorting table to prevent clumping and ensure even spacing before shaping. For traditional gnocchi, a patterned drum or stamp roller presses the surface of each dumpling, forming the signature ridges. These ridges aren't just for appearance. They help hold sauces and ensure the texture is consistent during cooking. The raw gnocchi are now ready for par cooking. Depending on the product type, they may enter a steam tunnel, boiling water bath, or continuous blanching system. For fresh gnocchi, a short steam treatment helps gelatinize the starch on the outer layer, setting the shape without fully cooking the interior. In the case of shelf-stable or refrigerated products, boiling is used for more complete cooking. The gnocchi travel through the system on mesh conveyors that allow water to drain or steam to vent. Those that float prematurely, often indicating trapped air or structural failure, are skimmed off and diverted. Finished gnocchi are cooled rapidly with air or chilled water sprays to stop the cooking process immediately. Cooling is followed by drying. Par-cooked gnocchi are passed through air tunnels or oscillating belts with forced, filtered airflow. This surface drying stage ensures the pieces don't stick together in packaging. In some configurations, a fine coating of semolina or rice flour is applied to further reduce surface tackiness. At this stage, the gnocchi are fully formed, partially cooked, and ready for packaging or freezing depending on the final product category. Fresh gnocchi are directed into multi-head weighing systems that portion exact quantities into pre-formed pouches. These machines calculate the best weight combination from multiple hoppers to ensure precision. Pouches enter a modified atmosphere packaging (MAP) chamber, where the ambient air is replaced with a mix of inert gases like nitrogen and carbon dioxide. This extends shelf life by inhibiting microbial growth and oxidative reactions. Sealing jaws then close each pouch under pressure, forming airtight seals. Pouches exit the MAP system and are immediately inkjet printed with production codes, expiration dates, and batch tracking information. For frozen gnocchi, the cooled pieces bypass MAP and instead travel to the freezing tunnel. This is a long conveyor system housed within an insulated chamber where fans blow extremely cold air across the product. The process is known as IQF, or individual quick freezing, which ensures that each gnocco freezes separately, avoiding clumps. Once frozen solid, the gnocchi are packaged in bulk or consumer-ready bags, sealed, labeled, and sent to deep freeze storage. Regardless of the format, every package goes through a metal detection and X-ray inspection station before final packing. These machines identify any potential contamination from production, like stray metal fragments from worn machine parts, and immediately reject any affected units. Packages that pass inspection proceed to robotic case packers, where arms equipped with vacuum grippers load them into cardboard boxes. The boxes are sealed, barcoded, and sent to automated palletizers that stack them according to optimized loading patterns. Each pallet is stretch wrapped and labeled with a traceable QR code or barcode, then entered into the warehouse management system. The final stage is cold storage and distribution. Refrigerated products are stored at 2 to 5 degrees Celsius, while frozen products are kept at 18 or colder. High-density shelving is managed by ASRS units, automated storage and retrieval systems that navigate the warehouse floor with programmed efficiency. When an order is placed, the system retrieves the correct pallet, stages it at the loading dock, and synchronizes it with outbound transport logistics. Goods are typically moved in temperature-controlled trucks that maintain strict thermal stability to prevent texture loss or microbial growth during transit. Quality assurance labs operate in parallel with the production floor. Technicians pull random samples from each batch to assess moisture content, cooking time, bite texture, and microbiological safety. These samples are cooked and evaluated for structure, flavor retention, and resistance to disintegration. Texture analyzers apply calibrated pressure to measure chew resistance, while high-resolution cameras measure shape retention after boiling. If a batch fails any parameter, the corresponding lot is flagged in the system and held for further review or disposal. Cleaning and maintenance operations take place in modular shifts. All lines are fitted with cleaning in place (CIP) circuits, automated wash systems that flush tanks, hoses, pumps, and valves with caustic solutions, hot water, and acid rinses. This ensures hygienic conditions even when production is running continuously. Key areas like mashing stations, flour feeders, and packing heads receive manual cleaning daily, and critical equipment like extrusion heads are dismantled, brushed, sanitized, and reassembled before every major production run. Throughout the process, every detail is monitored by supervisory control and data acquisition (SCADA) systems. These systems provide operators with real-time dashboards showing dough temperature, flow rates, extrusion torque, cutter speed, par cooking dwell times, and fill weights. Alerts and automated corrections ensure that even minute deviations are caught and resolved without interrupting production. Historical data is stored and reviewed to improve yield, reduce waste, and maintain traceability. From field harvested potato to the final sealed pouch or frozen bag, gnocchi production at factory scale is a precisely tuned sequence of heat, pressure, shaping, and preservation, all balanced to protect the soft, pillowy character that defines this classic product. What begins as humble starch and flour becomes thousands of identical dumplings per hour, delivered with perfect form, flavor, and shelf stability. Lasagna production in a factory is a multi-phase, highly integrated process that combines pasta sheet manufacturing, meat sauce preparation, cheese blending, layer assembly, baking or pasteurization, portioning, packaging, and cold chain logistics, all synchronized to ensure consistency, safety, and scale. Unlike dry pasta or single-element products, lasagna is a fully prepared, multi-ingredient dish. This makes its industrial production uniquely complex, requiring extensive machinery and tightly controlled automation to ensure that every slice mirrors the expected texture, flavor, and structure. The process begins with pasta sheet production. Durum semolina flour is delivered in bulk and stored in silos. From there, it moves through pneumatic conveyors into high-capacity mixing vats where it's combined with water under vacuum. This vacuum mixing reduces air bubbles and improves dough elasticity. The dough is then extruded into wide sheets using continuous sheeting rollers. These rollers compress and stretch the dough between pairs of calibrated rollers, gradually flattening it to a specific thickness, typically less than 1 millimeter. Optical thickness sensors positioned along the rollers feed data into a closed-loop control system that makes micro-adjustments in real time. The continuous pasta sheet is then guided onto a conveyor that passes through a high-temperature dryer tunnel. This dryer uses forced hot air to reduce surface moisture and firm the sheet slightly without fully cooking it, which gives it the pliability needed for layering. After drying, the sheet moves into a cutting system. Depending on the product specifications, a rotary knife assembly cuts the sheet into wide rectangular panels, each aligned with the intended tray dimensions. A rejection arm automatically discards any sheets that are torn, folded, or non-uniform. While pasta sheets are being prepared, the factory simultaneously produces the meat sauce. Ground beef is loaded into steam-jacketed kettles equipped with high-speed agitators. The meat is seared first, breaking it into small crumbles. Tomato puree, tomato paste, oil, chopped onions, garlic, herbs, and seasoning are metered into the kettles through automated valves. The sauce is simmered while being agitated to prevent scorching and ensure uniformity. During this time, inline temperature probes and brick sensors monitor thickness, sugar levels, and viscosity. Once the sauce reaches its target consistency, it's pumped through heated stainless steel pipelines into holding tanks that maintain it at a constant temperature until assembly. In a separate mixing area, the cheese component is prepared. Depending on the recipe, this may include a blend of ricotta, mozzarella, and parmesan. Ricotta is delivered in cooled totes and mixed with stabilizers, herbs, and sometimes eggs in vertical mixers to ensure even distribution. Shredded mozzarella and grated parmesan are stored in silo-like hoppers connected to vibratory feeders that portion out cheese by weight for each layer. Now begins the core of the lasagna production, layer assembly. This takes place on a continuous assembly line with moving trays or belt-mounted mold forms. Each tray or mold is sanitized prior to filling and travels under a set of ingredient dispensers. First, a measured amount of meat sauce is deposited into the bottom of the tray by a servo-controlled nozzle that moves in a sweeping pattern to ensure full coverage. A vacuum depanner then places a single pasta sheet on top, aligning it precisely over the sauce. This is followed by a ricotta deposit nozzle that pipes a uniform, ridged bead of cheese across the sheet, which is then smoothed by a vibrating spreader bar. Another pasta sheet is placed, and the cycle repeats: sauce, pasta, cheese, until the required number of layers is achieved. The top layer typically ends with sauce and a sprinkling of shredded mozzarella and parmesan dispensed by oscillating auger heads that shake cheese evenly over the tray surface. Before baking or pasteurization, some lines include a brief compression station where a flat paddle gently presses down on the lasagna to remove air pockets and improve bonding between layers. The fully assembled trays then move on to the thermal treatment phase. If the lasagna is intended to be frozen, the thermal step may be pasteurization, which involves heating the product just enough to kill bacteria but not fully cook it. For chilled or ready-to-eat versions, full baking is performed. Trays enter a convection oven that circulates heated air at over 180 degrees Celsius. The line speed, tray height, and internal oven temperature are all controlled to ensure even cooking from edge to center. Internal temperature probes inserted in sample trays verify that core temperature targets are achieved and held for a specific time to guarantee food safety. Once cooked or pasteurized, the lasagna must be cooled rapidly to prevent microbial growth and lock in texture. This is done through a tunnel chiller, where trays pass through zones of progressively colder air, sometimes supplemented by glycol-cooled plates that pull heat from the tray bottoms. The cooling process must reduce the product from over 80 degrees Celsius to below 5 degrees Celsius within a few hours, which is regulated by airflow, dwell time, and temperature differential. Sensors at the tunnel exit confirm that each tray meets cooling requirements. Once cooled, the lasagna is portioned and packaged. If individual servings are required, the tray is sliced by ultrasonic knives that vibrate at high frequency, cutting cleanly through dense layers without dragging or distortion. For family-sized portions, the entire tray may be sealed as is. Packaging formats include vacuum-sealed trays, film-sealed thermoformed, packages, or sealed and labeled foil trays, depending on the target market. Modified atmosphere packaging may also be used for chilled products to extend shelf life. Oxygen levels are flushed and replaced with inert gases before the final seal is applied. Each sealed package passes through a metal detector and X-ray unit to ensure it contains no foreign materials. It then receives an inkjet printed label showing the batch number, production date, expiration date, and a scannable code for traceability. The labels are verified by vision systems to confirm placement, readability, and correctness. Any mislabeled unit is automatically rejected into a separate channel. From there, packages are grouped into boxes using robotic case packers. These cases are palletized by automated arms that stack them in stable formations, alternating layers for weight distribution. Stretch wrapping units seal the full pallet, and each is tagged with a warehouse tracking code before being moved to cold storage. Depending on the product type, it may be stored in refrigerated or frozen conditions. Pallets are managed by automated guided vehicles that transport them to pre-assigned racks in high-density storage systems, where inventory software tracks position, age, and destination. Throughout this process, the factory uses a SCADA, supervisory control, and data acquisition system to monitor every critical variable. Dough hydration levels, pasta sheet thickness, sauce viscosity, cooking times, and packaging seal integrity are all tracked in real time. Historical data is stored and analyzed to identify patterns, correct deviations, and optimize throughput. If any parameter falls outside the designated range, alarms are triggered, and the system automatically isolates affected batches for inspection. Cleaning and sanitization cycles are embedded throughout the plant. Clean-in-place systems run through the pasta extruders, sauce kettles, and piping lines at scheduled intervals. Belts, mixers, and conveyors are cleaned using automated foamers and high-pressure rinsers between production runs, often overnight. This ensures the plant can shift from producing meat lasagna to vegetarian or gluten-free variants without cross-contamination. Every few hours, quality assurance teams perform manual inspections of randomly selected trays, assessing factors such as layer adhesion, ingredient distribution, flavor profile, pH level, and slice integrity. Cooking tests are conducted to see how the product behaves in a domestic oven or microwave, ensuring the consumer experience matches factory standards. The entire process, from flour and raw meat to finished boxed lasagna, is designed for speed, consistency, and hygiene. Trays of lasagna move continuously through a loop of automation, blending traditional culinary elements with industrial engineering. The meat must be savory but not greasy. The pasta should remain tender after reheating without breaking apart. The cheese should melt and set without seeping or becoming rubbery. Each of these qualities is maintained not through guesswork but through precise mechanical control over every movement, temperature change, and ingredient ratio. Dunkin' Donuts production starts with formulation of base dough using a high-capacity spiral mixer. Ingredients are loaded automatically through overhead dispensers connected to silos and tanks. The dry phase includes high-gluten wheat flour, sugar, salt, non-fat dry milk, and dough conditioners. Liquid components include water, whole eggs, vegetable shortening, and yeast. Ingredients enter the mixing chamber in a fixed order to ensure consistency. Flour is dispensed first into the bowl, followed by sugar and salt through calibrated rotary valves. Shortening is pre-melted in a jacketed vessel and dosed into the bowl using a metered pump. Liquid eggs are held in chilled tanks and dispensed through a pneumatic valve. Yeast is hydrated in a separate tank before being introduced into the mix stream. Mixing begins at a low speed to hydrate the flour and form gluten strands. The mixer transitions to a higher speed to fully develop elasticity. Total mixing time ranges between 8 and 12 minutes depending on batch size and target temperature. Bowl temperature is monitored through probes to prevent overheating. Once dough reaches optimal extensibility and temperature, it is discharged into a dough handling conveyor. This conveyor feeds a volumetric divider equipped with servo-driven pistons that portion dough into uniform units. Each portion is shaped into a ball using a rotary rounder. Rounded dough balls are transported by a belt conveyor into a multi-level proofer cabinet. Inside the cabinet, humidity and temperature are controlled to activate yeast fermentation. The dough rests for 30 to 60 minutes based on size and environmental conditions. After proofing, dough pieces exit the cabinet and enter a forming machine configured for ring shapes. A sheeter flattens each piece to a fixed thickness. A dual-blade rotary cutter stamps the dough into rings and removes the center to create the hole. Waste dough is automatically conveyed back to the hopper for reprocessing. Cut dough shapes are placed onto paper-lined proofing trays by a pick-and-place arm. Trays are loaded onto racks that feed into a secondary proofer tunnel. This tunnel maintains consistent humidity and temperature for final rise. Final proofing continues until dough height reaches preset targets. Proofed rings are then transferred onto a mesh belt conveyor leading into the frying system. The fryer is filled with vegetable oil, maintained at 190 degrees Celsius using immersion heating elements. The belt submerges each donut halfway and flips it midway to ensure even browning. Frying time is approximately 90 seconds per side. Excess oil is removed at the fryer exit using an inclined drip section. A vibrating shaker assists in shedding residual surface oil. Donuts proceed to a cooling conveyor that circulates ambient air over the surface to reduce internal temperature before finishing. Cooled donuts are sorted into finishing lines based on type. Plain rings move to the glazing station, which includes a curtain coater that pours warm sugar glaze over moving donuts. Excess glaze is recovered by a recirculation pump. Coated donuts pass under an air knife to remove drips and ensure uniform coating. For powdered sugar varieties, donuts are diverted into a tumbling drum. Fine sugar is dispensed into the drum continuously as donuts rotate inside. The tumbling motion creates full surface coverage. Sugar fines are filtered and reused through a vibratory sifter. Chocolate-coated donuts are transferred to an enrobing line. Melted chocolate compound is maintained at 38 degrees Celsius in a reservoir and pumped to a waterfall applicator. Donuts pass under the waterfall and receive a full coating. An inline cooling tunnel solidifies the chocolate layer. Filled donuts follow a different path. These start as solid discs cut from sheeted dough and proofed separately. After frying and cooling, each unit is aligned on a conveyor with a multi-nozzle injection machine. The filling system uses positive displacement pumps to inject jelly, custard or cream into each donut at a fixed volume. Nozzles penetrate the side and retract automatically after filling. Decorated donuts are moved to a robotic icing station. Each robot arm uses a temperature-controlled piping nozzle to apply icing patterns or toppings. Sprinkles are deposited via gravity-fed hoppers positioned above a vibrating grid. Icing is cooled rapidly with a chilled air tunnel to prevent smearing. Donuts requiring packaging are grouped using a photo eye sensor and placed into trays by a robotic loader. Trays are conveyed to the overwrapping station where a film is wrapped and sealed using a heated jaw. Packaged trays proceed to a labeling machine that applies product and date information. Donuts intended for retail stores are stacked into crates by a pusher arm. Crates are conveyed to a loading dock and stored in temperature-controlled bays before transport. Crate movement is sequenced based on product age to maintain first-in, first-out flow. Throughput is maintained by synchronizing mixing, proofing, frying, glazing, filling, and packing stages. Any discrepancy between steps is corrected by buffer zones built into the conveyor system. Sensors at each handoff point check for weight, position, and spacing. Dough properties are controlled through water temperature, flour hydration, and mixer speed. Yeast activity is adjusted using proofing time and sugar content. Fry color and texture are determined by oil temperature, dwell time, and surface evaporation rate. Glaze thickness is adjusted by flow rate and curtain gap. Chocolate viscosity is controlled with continuous mixing and temperature monitoring. Filling density depends on nozzle diameter and injection pressure. Sprinkle adhesion is determined by icing tack time and coating temperature. Rework dough is monitored to prevent excessive cycles which could affect gluten structure. Oil is filtered continuously through a mesh screen and replenished to maintain performance. Icing and glaze are discarded after exceeding hold time limits. Mechanical components are cleaned using a clean-in-place system for mixers and pumps. Fryer oil is drained and replaced after a fixed number of cycles. Filling stations are purged between flavor changes using heated rinse cycles. Donut size is kept uniform through automated cutting, proofing, and handling. Each unit is weighed inline using load cells before frying. Out-of-spec pieces are rejected by air jets and sent to waste bins. Color is monitored by optical sensors after frying and coating. Each production run is tagged with a digital identifier that tracks every batch of dough from mix to packaging. Operators interface with the line through touchscreen HM is that adjust process parameters and initiate recipe changes. The ring shape is maintained by cutter pressure, proofing time, and dough elasticity. Hollow centers expand predictably when gluten structure and gas production are balanced. Sidewalls form evenly when frying is performed at the correct temperature gradient. Filled donuts expand less during frying due to the absence of a central void. Filling volume is calibrated to prevent leakage and to ensure weight compliance. Injection heads are sanitized between runs using a self-cleaning piston flush system. Production of limited-time donuts uses custom molds or dies fitted to the standard sheeting line. These are swapped in and out using quick-release clamps mounted on the cutting head. All process conditions remain unchanged except for shape and possibly finish. The Dunkin' Donuts production process is defined by sequential control over dough preparation, shaping, frying, finishing, and packaging. No stage is manually operated after initial ingredient loading. All transfers are automated and time synchronized. Mechanical reliability is ensured through routine calibration of volumetric dividers, fryer controls, coating pumps, and injection systems. Sensors detect clogging, misalignment, or loss of temperature and alert the PLC for correction. Air quality around finishing zones is maintained using filtered ventilation that prevents icing contamination. Powder applicators are enclosed and use vacuum returns to contain sugar dust. Chocolate lines are enclosed and climate controlled to prevent blooming. Every donut passes through at least 8 separate mechanical systems before final packaging. Each system modifies dough, temperature, texture, filling, or coating in a defined and repeatable way. The outcome is a donut with precise dimensions, weight, color, and taste profile. Wendy's burgers begin with raw ground beef held in refrigerated stainless steel bins, fitted with auger-driven dispensers. The beef is pre-ground to a fixed particle size and loaded into a hopper positioned above the patty forming system. The patty forming machine uses a hydraulic ram to compress a measured quantity of beef into a square mold. The square mold consists of a cavity with sharp edges and adjustable depth to control thickness. The beef enters the mold vertically and is pressed to a target shape using downward force. A release plate ejects the formed patty onto a conveyor belt lined with a non-stick food-grade belt material. The patties travel on the belt to a pre-cooked staging zone where they are spaced using an optical sensor and gating arm. Each patty is indexed into a clamshell-style contact grill, which applies uniform pressure from above and below. The upper platen is heated with embedded electrical elements and lowered using pneumatic pistons. The bottom platen remains fixed and maintains a set temperature through thermal sensors. Cook time is controlled by belt speed and platen temperature. Average dwell time for each patty is between 100 and 120 seconds, depending on thickness and grill load. Internal patty temperature is monitored using inline thermal probes, which retract automatically after contact. Surface browning is caused by Maillard reactions accelerated by the grill temperature. Rendered fat drains through grooves in the lower platen and is collected in a drip pan. Excess steam is evacuated through a hood system positioned directly above the grill zone. Once cooked, the patty exits the grill and moves onto a staging tray held at a constant holding temperature using a heat lamp array. While patties are cooking, buns are prepared on a separate toasting line. Buns arrive from storage in trays and are unloaded onto a conveyor. The bun separation system uses rotating paddles to split top and bottom halves and align them face down on the line. Each bun half passes under a radiant toaster element, which operates at a fixed distance above the surface. Toasting time is determined by conveyor speed and element intensity. Bottom buns are toasted slightly longer than top buns to handle moisture from toppings. After toasting, buns proceed to the assembly belt where they meet other components. Burger toppings are prepared on parallel preparation lines. Leaf lettuce is pre-cut and washed, then stored in chilled bins and dispensed manually into bins along the line. Tomatoes are sliced using a rotary blade slicer that maintains uniform thickness. Slices are collected into trays and moved to the topping line by belt conveyor. Onions are peeled and cut using an automated ring slicer and loaded into shallow pans. Pickles are pre-sliced and held in brine-filled containers until use. Cheese slices are separated by a vacuum picker and fanned out onto a chilled tray. Condiments, including mayonnaise, ketchup, and mustard, are dispensed using trigger-activated pumps that release a fixed volume per stroke. Dispensers are calibrated to deposit evenly without spread beyond the bun area. Burger assembly begins with bottom buns moving along a belt aligned with the topping line. A pump dispenses mayonnaise directly onto the bun in a circular pattern. A square cooked patty is placed onto the bun using a precision-guided placing arm, or manually depending on station configuration. Cheese slices are placed directly on top of the hot patty, which softens the cheese slightly but does not fully melt it. Sliced tomato is added next by tongs or fingers placed at center alignment. A leaf of lettuce is layered over the tomato and adjusted to not overhang the bun. Onion rings are laid flat across the lettuce with no stacking. 2 or 3 pickle slices are placed side by side depending on diameter. Ketchup and mustard are dispensed in zigzag or dot patterns based on the specific burger recipe. The top bun is retrieved from its place on the parallel conveyor and inverted onto the built stack using a rotating arm. The complete burger is then moved forward to a wrapping station where it is enveloped in printed foil or wax paper. Wrapping is done by folding each side toward the center and then folding the base upward before rolling the package forward. Wrapped burgers are placed into holding bins arranged by product type. Bin trays are heated from beneath with radiant elements to hold temperature. Burger names and identifiers are shown on digital displays above each bin. The wrapped burgers are then pulled in the order of assembly requests from service or drive-through lines. For specialty burgers with additional ingredients, separate modules are added to the line. Bacon is pre-cooked in convection ovens and held on heated trays. Spicy toppings or sauces are dispensed through separate triggers. Extra patties are added by adjusting tray positions to align multiple cooked patties before final topping. The entire burger line is modular and designed for high throughput. Each step, from toasting to wrapping, is timed and paced using conveyor intervals and operator rhythm. Cooked patties are used within a fixed window to maintain thermal properties during assembly. The square patty shape aligns precisely with the round bun through placement guides. Cheese coverage is optimized by placing the slice diagonally across the square patty. Lettuce folds are standardized to reduce overhang and dripping. Tomato slices are inspected visually for diameter and replaced if undersized. Onions are separated into ring layers to maintain consistent thickness. Pickles are spaced to prevent overlap or bunching. Sauce volumes are adjusted using pump restrictors. Each pump cycle delivers a metered dose that is verified weekly by weight checks. Dispense angles ensure center placement with minimal deviation. Top bun pressure is measured periodically to confirm compression does not exceed tolerance. Overcompression can cause lettuce or tomato slippage. Wrap tightness is checked by torsion testing with digital force gauges. Grill platen pressure is balanced to avoid sear marks that penetrate too deeply. Contact time is calibrated to match patty water content and surface heat conductivity. Belt tension is maintained through spring-loaded rollers at both ends of the grill. Drip pan contents are filtered and cooled before disposal. Grease flow is measured to calculate fat loss per batch. Each tray of patties is weighed at intervals to confirm moisture retention and yield. Conveyor speed is set to match maximum output per cook zone. Bun toast time is synchronized to meet grill exit timing. Topping replenishment occurs based on tray weight thresholds detected by load cells. Tomato and onion prep stations are cleaned and reset every few cycles to prevent buildup. Cheese trays are kept below 5 degrees Celsius using chilled gel plates. Lettuce bins are sloped for continuous access without compaction. Burger stacking alignment is controlled by operator training and guided bins. Variants like double burgers use the same assembly line with secondary patty placement after cheese. Burgers with spicy or grilled ingredients use segregated stations to prevent flavor transfer. All process parameters are displayed on line-side screens for real-time monitoring. Operators adjust pump pressure, toast speed, and tray positions based on on-screen instructions. Each station is time-stamped to maintain consistency across shifts. Ingredient freshness is managed by rotation schedules and bin timers. No topping remains in use beyond its designated holding time. Each component has a separate preparation and service life which governs when trays are replaced. The square patty ensures uniform cooking and reduces edge shrinkage. Griddle contact area is maximized by flat pressing. Consistent doneness is achieved across all patties through center-out thermal profiles. The full Wendy's burger is formed by layering precise ingredient units in defined order. Each addition is made at a fixed position along the conveyor. The sequence ensures balance in flavor, weight, and thermal distribution. Assembly line pacing is regulated by burger type, quantity, and order load. Stack height is limited by bun compression threshold. Burgers are finalized within a tight time window to maintain optimal serving temperature. Pizza Hut. Pizza production begins with the preparation of pizza dough using automated high-capacity mixers. Each batch starts with high-protein wheat flour dispensed from overhead silos through a pneumatic conveyor into a stainless steel mixing bowl. Water is metered precisely from a temperature-controlled supply line and delivered into the bowl through solenoid valves. Instant dry yeast is stored in sealed bins and dispensed by auger into the bowl after water. Salt and sugar are pre-weighed and released into the bowl from vibratory feeders mounted above the mixer. Vegetable oil is pumped from a storage tank through a heated line and added last to ensure uniform distribution. The spiral mixer begins in a slow speed mode for 1 minute to hydrate the dry ingredients. After hydration is complete, the mixer shifts to high speed to develop gluten structure. Mixing continues for 8 to 10 minutes until the dough reaches a defined elasticity and target temperature range. The dough is discharged into a trough and transferred to the divider using a hydraulic lift arm. The divider uses a piston system to cut dough into fixed weight portions based on pizza size specifications. Each dough piece is rounded into a ball shape by a rotary rounding mechanism and deposited onto a lightly floured tray. Rounded dough balls are conveyed into a temperature and humidity-controlled proofing cabinet. The proofing stage allows yeast fermentation to produce gas and relax the dough structure. Temperature is held around 38 degrees Celsius and humidity near 85% to maintain surface softness. After proofing for approximately 1 hour, the dough is moved to a pressing station. Each ball is loaded onto a heated platen, which presses the dough into a disc shape. Pressing is done with a hydraulic top plate that flattens the dough to a specified diameter and thickness. Heat from the platen sets the shape and prevents shrinkage during later handling. Pressed dough discs are transferred to perforated baking pans or screens using a vacuum lifter. A light mist of oil is applied to the pan surface to prevent sticking. The dough and pan then move along a conveyor to the topping line. Topping application begins with sauce deposition using a volumetric piston filler. The sauce is pumped from a heated holding tank and dispensed in a spiral pattern starting from the center of the dough. A rotating disc beneath the pizza ensures even coverage without manual spreading. Shredded mozzarella cheese is stored in chilled hoppers and fed to a depositor via a vibratory conveyor. Cheese is distributed through rotating paddles that drop a measured weight evenly across the surface. Cheese coverage is calibrated to stay inside the dough border. Additional toppings are added in a fixed sequence depending on pizza type. Pepperoni slices are dispensed from a rotary carousel that places overlapping slices in concentric rings. Cooked sausage crumbles are metered through a hopper with a gate-controlled release. Vegetable toppings such as mushrooms, green peppers, and onions are added from separate hoppers using calibrated volumetric scoops. Bacon pieces and ham strips are dispensed from compartments, lined with agitators to prevent bridging. Olives are dropped from a chute fitted with a shaker plate to ensure even distribution. Pineapple chunks are added last and drained before dispensing to avoid excess moisture. Each pizza proceeds to the oven loading belt, which is synchronized with baking time and oven speed. The pizzas enter a conveyor oven with a stone or mesh belt and a controlled baking chamber. Top and bottom heat are separately adjustable using electric elements or gas burners. Baking time is generally between 6 and 7 minutes, depending on pizza size and topping load. The oven is divided into thermal zones which apply different temperatures to optimize crust and topping finish. Air circulation fans maintain uniform heat distribution within the chamber. Crust browning is controlled by bottom belt temperature and pan contact. Cheese melt is regulated by top zone intensity. Sauce bubbling and topping cooking are completed within the dwell time set by conveyor speed. Once baking is complete, the pizza exits the oven and is transferred onto a staging table with a heat-resistant surface. A metal lifter is used to remove the pizza from the baking pan if one was used. The pizza is then slid onto a cutting board positioned below a rocker blade cutter. The cutter is hinged to apply uniform downward pressure and is guided by slots in the board to maintain equal slice sizes. Standard cut configurations are 4, 6, or 8 slices depending on diameter. Each pizza is rotated to complete perpendicular cuts if required. Cut pizzas are transferred onto corrugated cardboard discs which serve as a support base. The pizza and disc are inserted into printed boxes by a sliding motion, which prevents topping displacement. Boxes are closed with a fold lock mechanism and stacked in batches on a heated shelf for holding. Specialty pizzas with cheese-stuffed crust use a different pressing process where cheese sticks are inserted into the dough edge before sealing. The dough is crimped mechanically to enclose the cheese along the perimeter. These variants are baked with slightly longer dwell times to ensure cheese softening. Thin crust pizzas skip the proofing stage and are sheeted directly after mixing. The sheeting line flattens dough using a 3-stage roller system that progressively reduces thickness. Sheeted dough is cut to shape using a rotating die and docked to prevent bubbling. It is transferred directly to the topping line without additional rise. Pan pizzas use thicker dough portions which are hand-pressed or machine-pressed into deep pans coated with oil. The oil creates a fried base texture during baking. These pans are baked longer at lower temperatures to prevent surface burning. Pizza Hut production lines are modular and can run multiple styles concurrently by using different lanes. Each lane is fed by a shared dough room and topping prep area. Toppings are staged in mobile chilled carts that are swapped based on menu rotation. Sauce preparation occurs in a separate area where tomato concentrate is blended with water and seasoning. The sauce is cooked in steam kettles and cooled rapidly before being pumped to holding tanks. Cheese is shredded in-house using rotary drum shredders or received pre-shredded in lined totes. Toppings are prepared using a combination of manual and automated methods. Whole vegetables are washed and sliced on rotating blade machines. Meats are pre-cooked and diced using high-speed dicers or crumblers. Toppings are loaded into color-coded bins and inserted into the topping line feed hoppers. Ingredient flow is monitored by load cells under each hopper, which signal refill triggers when weight drops below threshold. Each depositor is linked to a PLC that controls dispense rate, duration, and alignment. Pan and tray washing systems clean and sanitize bakeware after each use. Washed pans return to the pressing line in timed cycles. Conveyor belts are brushed and wiped at shift intervals to remove topping residue. All components of the pizza undergo mass balance verification to ensure recipe compliance. Each pizza's final weight is checked on a dynamic scale before boxing. Deviations trigger visual alerts and operator review. Conveyor speeds, depositor timing, oven temperatures, and cut configurations are all adjustable by touchscreen interfaces mounted on each station. Operators select pre-programmed recipes which load all parameters automatically. The dough formulation is calibrated to yield consistent rise, chew, and browning under standard conditions. Oil content determines tenderness, while yeast quantity controls gas production. Mixing temperature is adjusted based on flour temperature and ambient conditions to ensure batch uniformity. Cheese melt properties are influenced by moisture content and shred size. Sauce consistency affects spreadability and absorption into the dough. Topping order ensures base ingredient contact with heat for proper cooking. Every Pizza Hut pizza follows a defined flow from dough to boxed product. Each process stage adds a functional component that determines structure, flavor, or visual finish. Assembly is done in linear progression with limited manual input beyond topping reload and box stacking. Pizza format changes involve reconfiguring press molds, pan shapes, and depositor settings. Crust variants, such as garlic butter infused or herb seasoned, are handled by adding a post-bake brushing stage where liquid toppings are sprayed onto the crust using a rotating nozzle arm. Pizzas with drizzle finishes or sauces applied after baking use a dedicated finishing table where squeeze bottle applicators or peristaltic pumps add final ingredients. These finishes are applied before boxing and allowed to set for several seconds. Temperature retention in boxes is enhanced by vent hole design, box material thickness, and stacking method. Pizza integrity during transport is preserved by maintaining alignment and minimizing topping shift through controlled insertion. Lindt chocolate is produced in a tightly structured factory process that begins with the transformation of raw cocoa beans into ultra-fine, smooth, and creamy chocolate using specialized machines, proprietary techniques, and finely tuned timing sequences that preserve the delicate flavors of cocoa while eliminating bitterness and grit. The process begins when whole dried cocoa beans arrive at the factory in large bulk containers and are conveyed directly into storage silos built to maintain low humidity and a stable temperature to prevent any premature oxidation or moisture absorption. From these silos, the beans are measured out by weight and directed into a cleaning unit where vibrating screens, air classifiers, and magnetic separators remove stones, dust, string, and any foreign matter so that only clean beans proceed to the next step. The cleaned cocoa beans are then transferred to a batch roaster or continuous drum roaster, which exposes them to dry hot air with precise temperature control and rotation speed to ensure the beans are heated evenly from all sides. Roasting develops the flavor of the cocoa, reduces astringency, and darkens the color of the nibs inside the shell. The temperature and duration of roasting are carefully controlled depending on the variety and origin of the bean, and are adjusted based on moisture content and desired flavor profile. Once roasted, the beans are cooled rapidly using forced air to prevent over-roasting, and then they move to the winnowing machine. The winnowing process cracks each roasted bean and separates the outer shell from the nibs inside. This is done using mechanical rollers that crush the beans gently, and blowers that blow away the lighter shells while heavier nibs fall into collection bins. The winnowed nibs are what contain the cocoa solids and cocoa butter required for chocolate production. These nibs are directed into large grinding chambers where rotating steel drums or stone rollers crush them into a thick, dark, gritty paste known as cocoa liquor. This liquor is then pumped into a series of high-pressure hydraulic presses that separate the fat from the solids. The fat becomes cocoa butter, while the remaining cake is pulverized into cocoa powder. In parallel, whole milk powder, sugar, and additional cocoa butter are stored in bulk hoppers and prepared to be added to the chocolate base. The exact formulation depends on whether the chocolate being made is milk, dark, or white. For milk chocolate, cocoa liquor is blended with sugar, milk powder, and cocoa butter in large horizontal mixers until a uniform paste forms. This coarse chocolate mass is then sent to the refining stage. Refining involves passing the chocolate paste through a sequence of steel rollers that reduce particle size. Each roller set progressively narrows the gap, crushing sugar crystals and milk particles until they are reduced to between 15 and 20 microns. This ultra-fine particle size is critical for the mouthfeel of Lindt chocolate, ensuring there is no graininess when the chocolate melts on the tongue. The refined chocolate then moves to the conching stage, which is one of the defining steps in Lindt production. Conching is done in elongated mixers called conches that slowly knead the chocolate at elevated temperatures. typically between 45 and 80 degrees Celsius, for several hours or even days, depending on the recipe. The purpose of conching is to develop flavor and texture. During this phase, volatile acids and off flavors are driven off by heat and agitation, while the friction created by the mixing reduces viscosity and smooths the fat dispersion. This stage also transforms the aroma profile, eliminating any lingering bitterness or sharp notes and rounding out the flavor. In Lindt's process, conching is considered both a science and an art, and the parameters are adjusted delicately to reflect the cocoa origin, sugar type, and desired smoothness. Once the chocolate mass has reached the optimal flavor and flow characteristics, it is transferred to tempering machines. Tempering is a controlled heating and cooling cycle that aligns the cocoa butter crystals into a stable form, known as form Vi. This ensures that the finished chocolate will have a glossy finish, a crisp snap, and will not develop bloom or grayish streaks over time. In the tempering machine, the chocolate is first heated above the melting point of all cocoa butter crystals, then cooled to a point where only form 5 can reform, and finally reheated slightly to working temperature. During this process, precise control of temperature and agitation is vital. Tempered chocolate is now ready for molding or enrobing. For bar production, tempered chocolate is poured into polycarbonate molds, which are vibrated on automated shakers to remove air bubbles and allow the chocolate to settle evenly into every corner. The molds are then passed through cooling tunnels, where cold air gradually lowers the chocolate temperature until it sets and solidifies. For filled chocolates or truffles, the molds may first receive a thin shell of chocolate, which is cooled and then filled with soft centers like ganache, praline, or liqueur before being sealed with more chocolate and cooled again. Once the chocolate has solidified, the molds are inverted and gently flexed by mechanical arms or vibration plates to release the bars or pieces. These are conveyed through a final inspection area where high-speed cameras and vision systems scan for imperfections such as broken corners, air pockets, or deformed logos. Defective. Pieces are rejected automatically, and perfect pieces proceed to wrapping. Wrapping is tailored to the product type. Lindt bars are typically wrapped in foil, followed by an outer paper sleeve. Machines cut foil to precise dimensions, fold it tightly around each bar, and then apply the paper wrapper using hot glue or pressure-sensitive rollers. Filled chocolates and balls are often wrapped in twisted foil ends or sealed flow packs using high-speed rotary packaging machines. Each wrapped unit is date-coded and batch-labeled for traceability. The wrapped chocolates are grouped into cartons by robotic arms that use suction cups to pick and place items into retail display boxes or shipping trays. Cartons are sealed, labeled, and palletized on automated stations where stretch wrap secures the load for transport. Pallets are scanned, assigned barcodes, and stored in climate-controlled warehouses to preserve flavor and appearance. The ambient temperature is maintained between 15 and 18 degrees Celsius with low humidity to prevent sugar or fat bloom from forming. Throughout the entire process, every parameter, from roast temperature to conche duration to tempering curve, is logged and monitored by a central control system. Inline sensors track viscosity, temperature, and particle size, while samples are pulled regularly for lab testing. These lab tests include moisture content, flow behavior, flavor analysis, and crystal structure confirmation to ensure the chocolate meets Lindt's quality standards. Chocolatiers also perform sensory evaluations, tasting samples for balance, aroma, melt, and finish. Hygiene and cleaning are equally critical in the production line. Chocolate making equipment is cleaned between product changes using melted cocoa butter flushes, which push out remnants of previous batches, followed by food-grade detergent cycles and high-pressure rinse systems. All cleaning is validated with swabs and lab tests to prevent flavor, cross-contamination and microbial growth. In factories producing multiple chocolate types, changeovers are scheduled with precision to minimize downtime. Dark chocolate lines are usually run first, followed by milk and then white chocolate, since darker varieties are more difficult to flush from equipment. Any chocolate not meeting specification during changeover is reworked or diverted to non-retail uses. Each ingredient in Lindt chocolate is treated with care. Sugar is milled to uniform crystal size and stored in dry silos with dehumidifiers. Milk powder is kept in oxygen barrier bags to preserve freshness. Cocoa butter is melted and filtered through fine mesh screens to remove impurities before blending. Even inclusions like nuts or fruit are roasted or candied on site to preserve their crunch and freshness. And they're added via gravity feeders that deposit precise amounts into the mold as chocolate flows in. The finished product that arrives on shelves results from a careful sequence where every gram of chocolate has passed through dozens of machines, heat cycles, mixing steps, and quality gates to guarantee it matches Lindt's profile for shine, snap, aroma, and flavor. From bean to bar, the chocolate moves with purpose through a network of conveyors, tanks, rollers, pumps, sensors, and skilled calibration, ensuring that what ends up in the foil wrapper is not just chocolate, but a refined and deliberate experience. Hershey's chocolate is manufactured through a large-scale factory process that transforms raw agricultural ingredients into solid molded chocolate bars, using a continuous sequence of heating mixing, refining conching, tempering molding, and packaging that is engineered for consistency, scale, and shelf life. The process begins with the intake of whole, dried fermented cocoa beans that are sourced in bulk and delivered in freight containers to the processing facility, where they are offloaded using vacuum conveyors or bulk tipping systems into steel silos designed for moisture protection and temperature stabilization, so the beans are kept in ideal condition before production begins. From these silos, the beans are moved into a cleaning station where mechanical sieves air separators and magnetic traps remove foreign matter such as twigs, dust stones, and bits of string. And the cleaned beans then enter large batch roasters or continuous flow roasting drums where hot air is circulated through the rotating chamber to heat the beans evenly and activate the chemical changes responsible for chocolate flavor and aroma. The exact roasting temperature and time are carefully controlled to vary the flavor strength depending on the blend being produced, and the roasted beans are then cooled quickly using forced air or vacuum systems to lock in the desired profile and prevent overdevelopment. Next, the cooled roasted beans pass through a cracking and winnowing machine where roller blades break the shells apart, and airflow systems separate the lighter papery husks from the heavier cocoa nibs, which contain the actual cocoa solids and cocoa butter required for chocolate production. The separated nibs are collected and sent to grinding chambers, where heavy granite rollers or steel grinders crush them into a thick, dark paste known as chocolate liquor, which is not alcoholic, but simply refers to the pure ground state of cocoa solids suspended in their own fat. At this stage, the chocolate liquor is held in heated storage tanks, where it can be separated into cocoa butter and cocoa solids if necessary, using hydraulic presses or used directly in chocolate mass formulation. The chocolate base used for Hershey's milk chocolate typically includes chocolate liquor, sugar milk, powder, cocoa butter, and sometimes emulsifiers to improve flow properties. And in this stage, these raw materials are measured precisely using load cells and volumetric dosing systems before being transferred into industrial blenders, where they are mixed at high speeds into a coarse brown paste. The sugar crystals are still relatively large at this point, and the milk powder has not fully hydrated, so the mixture is lumpy and thick. But the goal of this step is to distribute the ingredients uniformly before refining. The refining process consists of passing the chocolate paste through a 5-roll mill or similar refining system which crushes and shears the mixture repeatedly until all particles are reduced to between 15 and 20 microns in size, which is below the threshold of perception on the human tongue and is responsible for the smooth texture of finished chocolate. The refined powdery mass exits the rollers as dry flakes, which are collected and fed into large conching vessels, which are long horizontal mixers with heavy paddles that knead the chocolate continuously while applying gentle heat. Conching is one of the most important steps in the process and can last from several hours to a full day, depending on the batch size and the desired flavor characteristics. And during conching, the frictional heat softens the cocoa butter, allowing it to coat sugar and milk particles completely. While the mixing action evaporates unwanted volatile acids that contribute bitterness and also promotes chemical bonding between ingredients that gives chocolate its rounded flavor and creamy mouthfeel. In Hershey's process, this stage may include the addition of flavor compounds or the use of proprietary heating profiles that contribute to the distinctive, sweet, slightly tangy note associated with their milk chocolate. After conching, the now liquid chocolate mass is pumped through a fine mesh filter to remove any remaining solids and then enters the tempering system, which is a temperature-controlled series of heat exchangers and holding tanks that bring the chocolate through a controlled heating and cooling cycle designed to stabilize the cocoa butter crystals into the desired form V structure, which provides gloss snap and resistance to fat bloom. The tempering process requires careful monitoring of viscosity temperature, shear rate, and time to produce a chocolate that will remain stable during storage and distribution. Once tempered, the chocolate is moved into the molding line where it is dispensed into bar molds, using precise portioning heads that fill each cavity to the exact weight required. And the filled molds are shaken on vibrating tables to eliminate air bubbles and ensure even distribution of the chocolate across the mold. The molds then pass through a cooling tunnel where refrigerated air is circulated in stages to gradually bring the chocolate down to the release temperature, allowing it to solidify without developing stress cracks or surface bloom. When the chocolate has fully set, the molds are inverted and the bars are ejected using mechanical arms or flexing systems that pop the finished bars onto conveyor belts for inspection. Every bar passes under a series of vision systems that scan for surface defects, broken edges, misaligned logos, or irregular thickness, and any bar that fails inspection is automatically diverted for rework. Acceptable bars move forward to the wrapping section, where high-speed machines fold foil or film around each piece and seal it using heat or pressure depending on the packaging format. Paper sleeves or cardboard cartons are then applied and printed with product information barcodes and expiration dates using inline inkjet or laser printers. Wrapped bars are grouped into shipping cases by robotic packing arms and loaded onto pallets, which are stretch wrapped and labeled for traceability before being moved into temperature-controlled storage rooms maintained between 15 and 20 degrees Celsius to preserve texture and flavor. From this point, the bars are distributed through refrigerated trucks or ambient carriers depending on shelf life and destination requirements. In parallel with production, the entire process is monitored by sensors that record key data at every stage, from ingredient weight and tank temperature to roller pressure and mold cavity fill speed. And this data is fed into a centralized quality control platform that logs all production variables and triggers alerts if any parameter drifts outside the approved range. Quality assurance teams sample bars from each batch and test them in laboratories for moisture content, melt profile, flavor, strength, hardness, and microbiological stability. And these tests ensure that every bar maintains the same quality level regardless of where or when it is produced. All equipment used in the chocolate production line is constructed from food-grade stainless steel and is subject to strict sanitation protocols between product runs. Clean-in-place systems flush liquid chocolate from pipes and tanks using melted cocoa butter, followed by hot detergent solutions and sterile water rinses, and these cleaning cycles are verified using swab tests and microbial analysis before the next production run begins. During cleaning, mechanical components such as belts, pumps, and seals are inspected for wear and lubricated with food-safe oils to maintain performance and prevent contamination. Because Hershey produces multiple chocolate types, including dark white and flavored variants, the factory must perform regular changeovers that are scheduled with precision to minimize waste and avoid flavor crossover. And this is typically done by running from the lightest product to the darkest, so that any residual ingredients are less likely to impact flavor in the next batch. Storage of ingredients is just as critical as processing, and milk powder is kept in dehumidified silos lined with oxygen barriers, while cocoa butter is stored in heated jacketed tanks that maintain a constant liquid state, and sugar is held in dry bins fitted with vibratory feeders to ensure consistent flow into the mixers. Even inclusions like almond toffee or cookie pieces are added through dedicated feeders designed to introduce solids at the molding stage without disrupting flow or causing jams. From beginning to end, Hershey's chocolate production line is a finely tuned balance of mechanical engineering, food science, and sensory evaluation, where the transformation of beans into bars depends on maintaining strict control over texture, flavor, and structural integrity. The iconic bars that result are the outcome of thermal history, particle refinement, fat crystallization, and packaging precision that together produce a chocolate that is consistent across millions of units and recognized by consumers around the world. Godiva chocolate production begins with the careful handling of raw cocoa beans, which arrive at the factory in bulk loads from cocoa growing regions and are stored in cool, dry silos that prevent moisture contamination, oxidation, and pest activity. These beans are first cleaned through mechanical sifters that remove stone shells, dust, and organic debris using a series of vibrating screens, suction fans, and magnetic traps. Once cleaned, the beans are weighed and portioned by automated systems and conveyed to the roasting chambers, which are precision-engineered rotating drums capable of uniform thermal penetration across the entire mass of cocoa beans. Roasting is the first flavor-developing stage in the chocolate-making process, and in the Godiva production method, it is carried out at moderate temperatures for extended periods, which helps preserve the aromatic volatiles while driving off unwanted acidity and bitterness. Each batch is roasted based on its origin and moisture level, with constant temperature regulation using internal thermocouples that feed data to a computerized control system. Once the beans are fully roasted, they are immediately cooled with forced air systems that halt the roasting curve and stabilize the volatile compounds formed during heating. The next step is winnowing, which involves cracking the roasted beans open to separate the brittle shells from the cocoa nibs inside. The beans pass through a mechanical cracker that gently fractures them, and a pneumatic winnower that blows the lighter shells away while the heavier nibs fall into collection bins. These nibs are the core ingredient in all chocolate and contain both cocoa solids and cocoa butter in their natural ratio. The nibs are routed to a pre-grinding unit where rotating stone rollers or steel discs crush them into a thick, gritty paste known as cocoa liquor. This liquor is heated slightly to reduce viscosity and then transferred to high-pressure hydraulic presses that squeeze out the cocoa butter, leaving behind a dense cake of compressed solids which are ground into cocoa powder. For milk chocolate production, the cocoa liquor is blended with refined sugar, high-quality milk powder, additional cocoa butter, and in some recipes, a hint of vanilla or lecithin, which acts as an emulsifier. Each ingredient is dosed using gravimetric feeders and poured into large, high-speed mixers where they are combined into a smooth, uniform brown paste. This initial chocolate mass is far too coarse to be palatable, so it is sent to the refining system. This consists of a 5-roll mill where the mixture passes between sets of rollers that progressively reduce the particle size down to below 20 microns, creating a texture that feels smooth and creamy on the tongue. After refining, the powdered chocolate mass is transferred into conching machines, which are large horizontal vessels with internal mixing blades that work the chocolate slowly while applying gentle heat. This process can take anywhere from 12 to 24 hours, depending on the desired flavor profile, and is critical for developing the smooth texture, deep aroma, and balanced flavor that distinguishes Godiva from other mass-market chocolates. The conching action evaporates undesirable acids and moisture while distributing the cocoa butter evenly over every particle, which contributes to the distinctive mouthfeel and melt of the final product. Once conching is complete, the chocolate is sent through a filtration unit to remove any remaining impurities and then proceeds to the tempering stage, which is one of the most technically precise parts of the entire process. Tempering involves heating the chocolate to above its melting point, then cooling it down to initiate the formation of stable cocoa butter crystals known as Form 5, and then slightly reheating it to a working temperature, where those crystals can be maintained in suspension. This controlled crystallization ensures that the finished chocolate will have a glossy sheen, a crisp snap when broken, and a long shelf life without the development of sugar or fat bloom. The entire tempering process is carried out in enclosed stainless steel tanks equipped with agitators and digital thermostats that keep the temperature profile exactly within a 1 degree tolerance. The tempered chocolate is now ready for molding or enrobing. For solid chocolate bars or shapes, the tempered chocolate is poured into precision-engineered molds made of food-grade polycarbonate. These molds are vibrated to remove air bubbles and ensure that the chocolate spreads evenly into every corner and detail of the design. The filled molds then pass through a cooling tunnel that gradually lowers the temperature, allowing the chocolate to solidify and contract slightly so it can release cleanly from the mold. The pieces are then turned out and conveyed to the packaging line. For filled chocolates like pralines, truffles, and caramels, the process adds additional steps. The mold is first coated with a thin layer of tempered chocolate using spinning or tilting mechanisms to create a uniform shell. This shell is cooled just enough to firm up and then filled with liquid centers like ganache hazelnut paste or fruit cream using precision nozzles that deliver exact volumes to each cavity. Once filled, the chocolates are sealed with a final layer of chocolate and sent through a second cooling tunnel to solidify completely. These filled chocolates are then demolded and sent to wrapping. Enrobed chocolates, such as chocolate-covered nuts or biscuits, are passed on a conveyor belt under a waterfall of tempered chocolate where they are coated completely and pass under a vibrating plate that ensures even coverage and allows excess chocolate to drip off. The enrobed pieces then pass through a cooling tunnel similar to the molded chocolates where the coating solidifies uniformly. Wrapping is carried out using high-speed automated systems that use foil or flow wrap depending on the product. Each chocolate is first wrapped in an inner layer to preserve freshness and then given an outer wrap or box depending on whether it's a single piece or part of a collection. These wrappers are applied using thermal sealers and folded precisely by mechanical arms to maintain presentation quality. The finished chocolates are grouped into assortments using pick-and-place robots that load them into rigid trays or decorative boxes, which are then closed, labeled, and shrink-wrapped for transport. Throughout the entire production process, quality control is integrated into every stage. Inline sensors measure parameters like particle size, viscosity temperature, and moisture content. Random samples are taken and tested for flavor consistency, flow behavior, microbiological safety, and visual appearance. Each batch is tracked from bean to box using barcode systems and digital batch records, which allow full traceability and accountability. Any deviation from the strict specifications results in automatic rejection and investigation to maintain the high quality associated with Godiva. Packaging lines are designed not only for speed, but also for delicate handling. chocolates are not simply dropped into boxes, but placed gently by grippers or vacuum arms to prevent any scuffing or deformation. Seasonal and limited edition boxes are assembled by dedicated packaging stations that include decorative inserts, gold leafing, or ribbon application, all of which are coordinated with the central production database to match inventory with demand forecasts. Finished products are palletized automatically and moved to cold storage areas where the ambient temperature is held between 15 and 18 degrees Celsius with low humidity to protect against fat bloom sugar crystallization or flavor degradation. Logistics systems monitor inventory in real time and coordinate dispatch using climate-controlled vehicles that ensure the chocolates arrive at retail destinations in pristine condition. Factory sanitation is handled with clean-in-place systems for all enclosed equipment and rigorous manual cleaning protocols for all external surfaces. Between product types, especially when transitioning from dark to milk or white chocolate lines, are flushed with cocoa butter and inspected using allergen tests to confirm no cross-contamination occurs. Equipment such as molds tempering tanks and piping is made from food-grade stainless steel and is subject to frequent validation, including swab tests, microbiological plating, and ATP analysis. Each product that leaves the factory reflects a meticulously controlled combination of mechanical design, sensory expertise, thermal precision, and ingredient handling, all executed on a scale that allows handcrafted quality to meet global demand. Godiva's reputation depends on this balance, where artistry meets automation, where every bar and truffle is not only shaped by steel and steam, but guided by formulas and feedback that ensure every box offers the same refined, luxurious experience no matter where it is opened.